Testing. Testing, testing, testing. Testing. Testing, 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 testing. Testing. Testing, testing. I don't know if this is the right microphone. Just double check here. Okay, try this. Testing. Testing. Okay, I think this works. Alrighty. How's it going, Luke? How's it going, Bob? Hope you guys are having a good Monday. We're going to start off this week with a little bit of a computer vision stream today. So we're going to be reading this paper called 3D Gaussian Splatting for Real-Time Radiance Field Rendering. This paper has been making the rounds around the internet because it is a different way of doing kind of 3D rendering, kind of like a NERF, if you want to think of it that way, but in a different way. And it's basically using these Gaussians. So a different kind of prior than NERFs, which is resulting in a kind of completely different look. And apparently it's faster, it's better, and I don't know. That's what we're going to figure out, is we're going to read this paper and see if they're actually correct in their claims that it's better and faster, or whether they just cherry-picked a bunch of stuff and that's why it looks better. So 8th August 2023, relatively recent work coming out of INRIA, Université Côte d'Azur. I don't know where that is. Université Côte d'Azur. Here we go. It's actually down south of France. All right. It's probably where the cool kids go. It's probably very nice weather. Max Planck Institute is quite famous, though. So this is, I guess, secondary advisor from the Max Planck Institute. All right. So here in the picture, they have a picture of a bike. A couple different variants that they're comparing to. Of course, ground truth is going to be the actual image. You have some neural radiance field. You have planoxels. This is instant neural graphic primitives, I think, is instant NGP. And then this one here. And peak signal to noise ratio, about the same for all of them, to be honest. And the train time, I think that's the money here, is 48 hours for this NERF here versus 51 minutes for this 3D Gaussian Splat. John Egan, how's it going? Okay, so let's just dive right into this abstract. Radiance field methods have recently revolutionized novel view synthesis of scenes captured with multiple photos or videos. So the whole point of something like a NERF or something like this technique is creating novel views, which basically means new images from a different point of view of a scene. So a scene is just any kind of 3D environment with some objects in it. Maybe it can be object-centric, in which case there's a central thing, or maybe it's just not object-centric, which means maybe it's a picture of an inside of a room, right? And most of the stuff is on the walls and on the outside. But you have multiple pictures of this scene or this object, and you want to be able to create some kind of abstract representation of that scene or that thing such that you can create novel views of it, right? So 2D images of that thing, but from a different angle of which you didn't have a picture or photo, right? So that's what novel view synthesis of scenes captured from multiple photos and videos is. Okay. However, achieving high visual quality still requires neural networks that are costly to train and render. So this is kind of a dig on neural radiance fields, where you are using a neural net to learn a specific radiance field that is encoding the image or the color and the opacity of different points in space. Right, that's where the whole vector field comes from. And unfortunately for NERFs, you have to basically train a neural net for every single scene, every single object, and even those scenes and objects are at a specific point in time. So if you were to change the lighting, if you were to move objects within that scene, you would have to train a new NERF. So it's kind of annoying to have to do that. For unbounded and complete scenes rather than isolated objects, so this is kind of their way of describing what I'm describing as object-centric. So NERF, computer vision, if I could spell right. But this would be the example of something that's object-centric, right? There's a single object here in this scene. It's just this little Tonka truck, and you have it from a variety of different angles. This is also object-centric. You see this man's face. But this scene here is, I think some of the scenes that they're considering are not necessarily going to be object-centric. So the stuff is all kind of more splayed out, and it's usually harder to do those scenes rather than these object-centric scenes. So this would be an example of a not object-centric scene. You see how much harder it is to do that. Okay, 1080p resolution rendering. No current method can achieve real-time display rates. So yeah, you can't really do that with NERFs. That's why they're not super super mainstream at this point, right? Video games still use your texture and meshes. They're not using NERFs, and part of that is because the real-time isn't quite there yet. We introduce 3 key elements to allow us to achieve state-of-the-art visual quality while maintaining competitive training times, and importantly allow high-quality real-time novel view synthesis. So this basically means that once you've created this representation of the scene, can I get these novel views in real time? How's it going, Christopher? Testing. First, starting from sparse point clouds. So sparse point clouds is just a point cloud that is produced, or that doesn't have a lot of points, right? It's sparse. Produced during camera calibration. We represent the scene with 3D Gaussians. I think this is going to be the cornerstone of this entire paper, is they're basically going to, rather than representing the scene as a radiance field, which is what a NERF does, they're going to represent the scene as a set of 3D Gaussians. So a different prior or different starting point, different assumption that they're going to use for this entire thing. That preserve desirable properties of continuous volumetric radiance fields for scene optimization while avoiding unnecessary computation in empty space. There is a bunch of tricks that people have come up with for NERFs that also avoid unnecessary computation in empty space, and the continuous here means that you'll be able to evaluate at every single point in this space or every single pixel once you actually decide on the novel view that you want to render. We perform interleaved optimization and density control of the 3D Gaussians. Okay, so multi-step optimization process, notably optimizing anisotropic covariance to achieve an accurate representation of the scene. Okay, so some kind of tricky optimization objective, maybe a combination of multiple losses and objectives in possibly multiple steps that are alternating back and forth. Generally, that's not necessarily a good thing if you have a complicated optimization process with different loss functions and different kind of back and forth steps. That usually means it's going to be slower, it's going to be more annoying, it's going to be harder to implement, it's going to be harder to understand. So we'll see how bad it is for this paper. Third, we develop a fast, visibility-aware rendering algorithm that supports anisotropic splatting and both accelerates training and allows real-time rendering. So I think the splatting, which is here at the beginning, is, I'm not exactly sure if there's a formal definition for that, but scrolling through this paper, I think what they're referring to is that any object, so let's say that this little black blob thing here is the actual object you want to create or represent with these Gaussians, and these Gaussians here represented as 2D Gaussians as these green splats, I guess. But you can combine them and then create kind of a representation of that object with these Gaussians. So you can see how here they took this Gaussian here and they stretched it out in this dimension, and then they stretched it out in that dimension, and they rotated it a little bit, and then you can create this kind of, I guess, representation of it. Is there a more formal definition of splatting? What does splatting mean in the context of Gaussians? We'll see. We'll see what ChatGPT tells us here. Okay, let's go back up to the top. So that was the abstract. We've got some keywords here. We've got some addresses, some emails if you guys want to spam these people. And let's look at the first figure here. Our method achieves real-time rendering of radiance fields with quality that equals the previous method with the best quality, while requiring optimization times competitive with the fastest previous methods. Okay, so it's fast and high quality. I guess that's the metrics that you care about. Key to this performance is a novel 3D Gaussian scene representation. That's what we're going to figure out here with a real-time differentiable renderer. So differentiable renderer is a render that you can take the derivative of, which offers significant speed up of both scene optimization and novel view synthesis. For comparable training times, we achieve similar quality. While this is maximum quality, training for 51 minutes, we achieve state-of-the-art quality. Okay, we'll see what they use to determine that their quality has reached state-of-the-art. Unfortunately, for quality, especially for images, it's very subjective, and there's a variety of different quantitative metrics that people can use to determine the quality of things, but at the end of the day, those quantitative metrics are never as good as a subjective quality measure. So state-of-the-art in quality is not a super strong claim because you can just find some random quantitative quality metric that makes the claim for you, but it could be the case that humans looking at your thing don't agree that it's actually high quality. Okay. Just saw the sample output on the mentioned link. So cool they are able to achieve such high FPS with low training time. Yeah, it should be interesting, but sometimes it's like these papers, like there's so much cherry picking, there's so much kind of concealing and misdirection that you gotta actually go through them to see if they're actually doing what they say they're doing. Okay, meshes and points are the most common 3D scene representations. So meshes are what you think of when you think of a something in a video game, right? It's basically a collection of points that are connected, and then you basically have these little triangles, and those create the rough 3D shape of an object. But points are part of a mesh, and then usually with meshes you have what are called textures, which are basically an image that wraps onto a specific mesh, and that's 99% of video games, and CGI is done using those types of representations because they are explicit and a good fit for fast GPU and CUDA-based rasterization. So this is the original purpose of GPUs, right? GPUs were originally for graphics processing. That's what graphics processing unit means, right? And GPUs were designed to basically render quickly these texture and mesh representations of objects and scenes because they're very good at basically, once you have these meshes, right, these little triangles, mesh triangles, right? And you have a light source, you can say, okay, well, if the light is coming in from this angle, and I know that the surface has this particular angle because I know the exact angle based on the fact that it's a triangle and it has a normal vector, then I can calculate the way that the light is going to bounce, and I have some properties of this surface, and I have the specific texture, which is telling me the color of that surface, and therefore I can tell you what this is going to look like from this exact point of view at this exact angle. And that kind of physics-based rendering is what all video games use, but the key reason I'm bringing that up is that that type of physics-based rendering is just a bunch of calculating simple vectors and the path of light and all of that, and those simple operations. Someone at some point said, hey, why don't we create a specific processor that we can attach to your normal computer, and this processor will be able to basically parallelize these simple computations so that we can get you the right pixel colors based on these textures and meshes. And that company was NVIDIA, and eventually they made these GPUs, and then someone was like, wait a second, these GPUs are also very good for training neural nets. So kind of it all feeds into each other. That's a big problem in super resolution papers. PSNR and other metrics are often not well correlated with perceived fidelity. Yeah, agreed, Luke. I think PSNR, Frechet inception distance, even structural similarity index, SSIM, that's another one. Like, none of those are true quality, like end-all be-all numbers. Okay. In contrast, recent neural radiance field methods built on continuous scene representations. So a continuous scene representation is a representation of the scene that is continuous. You can evaluate it at every single point in space, right? A NeRF defines a little 3D volume. You could write a little cube of 3D space, and you can say at any point in that space, you can say what is the color and the opacity, which is just a fancy way of saying how see-through is it at this point in space. Typically optimizing a multi-layer perceptron. The multi-layer perceptron that they're referring to here is this one here in the NeRF. So in the NeRF, you're training this little neural network here, f of theta, and each of these, you could think of the little layer, and there's 3 layers here in this figure, so a multi-layer neural network, which is also called a multi-layer perceptron. The perceptron is just kind of a historical legacy term. That's what the original guy called it, but it's just a neural network. Using volumetric ray marching, this is the actual way that they render the NeRF, right? So ray marching is this, what's going on here. This red line is a ray, and then you're marching along that ray, and you can see how you're sampling at different points along your continuous scene representation. Okay, similarly, the most efficient radiance field solutions today built on continuous representations by interpolating values stored in voxels or hashes or grids or points. Okay. While the continuous nature of these methods helps optimization, the stochastic sampling required for rendering is costly and can result in noise. So the stochastic sampling required for rendering, they're talking about how you have to basically sample little points inside this volume. And you can see how for every pixel in this novel view that you want to generate, you need to create a ray. And then for that ray, you need to sample a bunch of points. So you can imagine how if you want a really high resolution image here, you're going to have a ton of pixels, and each of those pixels is going to have a ton of points along the ray, so it can kind of get out of hand very quickly. We introduce a new approach that combines the best of both worlds. Our 3D Gaussian representation allows optimization with state-of-the-art visual quality. Here they are again, putting state-of-the-art in their research paper 500 times so that they can get approved and not rejected by the paper reviewers. And competitive training times, while our tile-based splatting solution ensures real-time rendering and state-of-the-art quality. So tile-based here kind of indicative that they're probably going to do it in such a way that you don't have to do it per pixel like a NeRF. You can maybe they're going to break up the image into these little patches or tiles and then get all of the pixels in the tile at once or something like that. Blah, blah, blah. Our goal is to allow real-time rendering for scenes captured with multiple photos. Okay, so I take a bunch of pictures of some scene or some object, and then I render in real time new images of that scene or that object. And create the representations with optimization times as fast as the most efficient previous methods. Do you need to know the exact camera position like a NeRF? Probably. They haven't mentioned it yet, but pretty much always with these things, if you can come up with an alternative to NeRF and to these 3D Gaussian splatting techniques that do not require camera positions and works just as well, that would be huge. That would be absolutely massive, because all of these techniques right now require a camera position for every single picture that you write. The multiple photos or videos need to have precise camera positions. Usually that's done with an older technique, actually right here, a camera calibrated with structure from motion, right? But the structure from motion is itself not perfect, right? That's an actual older algorithm that says, okay, given these cameras, I'm going to find these little points, and then I'm going to kind of use rough triangulation to give you an idea of kind of where the camera image is, but I don't actually know exactly where the camera was. I'm just giving you a guess. So all of these techniques, whether it's a NeRF or this Gaussian splatting, are all based on a guess. So if you can figure out a technique that doesn't require you to start from that guess, which has some noise in it, then that could be huge. Okay, so they're comparing here to NeRF, which requires 48 hours of training time, but this is kind of like the worst possible NeRF. Like, I think I've seen NeRFs, we've even read some papers on this channel where there's NeRFs now that are much faster. They have all kinds of fancy, like, kind of ways of voxelizing and hash functions in such a way so that doesn't actually take that much time to train anymore, but it still takes time to train, which is annoying. Okay. Solution builds on 3 main components. So the first component is going to be these 3D Gaussians. which are their prior that they're going to use to represent this scene. We start with the same input as previous nerfs. Camera is calibrated with structure for motion, which is going to introduce noise, unfortunately, and initialize the set of 3D Gaussians with the sparse point cloud produced for free as part of the SFM process. Okay, so this structure for motion process is going to basically say, here are the pictures that you gave me, here are some points in those pictures that might correspond with each other, and because I can basically do triangulation, basic camera geometry, I can tell you here are the points that I think are real 3D points in space, and those are the sparse points, and it sounds like they're basically going to initialize the set of 3D Gaussians to those points, or to those sparse points produced by the SFM. In contrast to most point-based solutions that require multi-view stereo data, we achieve high-quality results with only SFM points as input. Okay, so I guess multi-view stereo data. Stereo refers to 2 cameras, multi-view even more cameras, right? So that's just going to increase the accuracy of these points. Note that for NERF synthetic dataset, our method achieves high quality even with random initialization. So a NERF synthetic dataset, what they're talking about is that in a lot of the NERF papers, they're not actually using real scenes. They're basically using 3D objects. And the reason they do that is so that they can basically take pictures from every single angle and they know the exact camera position, right? If you're doing this synthetically, which means that you're doing this in a video game, you can put the camera wherever you want, right? So you can put the camera on this side and you know that it's perfectly 90 degrees. And you can put the camera on this side and you know that it's perfectly negative 90 degrees. So a lot of these NERF papers use synthetic data sets because it allows you to basically have a perfect picture and camera position for everything. So this ship, this Lego, this microphone, these materials, these are all perfect synthetic data sets. So they're saying that if we actually use the same synthetic data set that most of these NERF papers use, we can actually achieve the high quality look with random initialization. So random initialization refers to the where do you choose to put these 3D Gaussians. Okay, we show that 3D Gaussians are an excellent choice since they're differentiable volumetric representation. Differentiable means that you can take the derivative, they're continuous, there's no discontinuities there. It's like smooth, and then there you go, smooth. Everybody wants smoothness. But they can also be rasterized very efficiently by projecting them to 2D. Okay, so that's kind of interesting. Probably the 2D, projecting to 2D, what they're referring to is that they're going to have a 3D representation, kind of like you have in this NERF, where is it? 3D representation, but then you have this 2D projection, which is the image. So any 2D image is a 2D projection of a 3D scene. So it sounds like they're going to be using these 3D Gaussians, but then projecting them into 2D to get the actual final image, which is the novel view that the quality is going to be determined by. By applying standard alpha blending is alpha is basically the see-throughness of something. Alpha blending is if you guys ever use like Adobe Photoshop or something like that, that's the same kind of idea. Like certain things are more see-through than other things, and allows you to put a bunch of things together on top of 2D that are at different layers and then have one final image. Using an equivalent image formation model as NERF. Okay, I don't know what they mean by the image formation model in NERF. The second component in our method is optimization of the properties of the 3D Gaussians. So these 3D Gaussians are going to have a 3D position, an opacity. Okay, so that's actually similar to the NERF, an anisotropic covariance. So the covariance is basically the variance along each of the 3 spatial dimensions, because this is a 3D Gaussian. So the variance is basically the spread of a Gaussian, right? So how wide it is. Variance of 2D Gaussian. Let's see if there's a good pick for this. Yeah, here we go. So if you have a 1D Gaussian, there's only one variance, right? So here you have a mean, and then you have the variance for a 1D Gaussian. If you have a 2D Gaussian, you have 2 possible variances, right? Because you have the variance on x and the variance on y, and that's what this term here is, right? So this is the variance in x and the variance on y. That's what the diagonal is. But this, the covariance, and specifically the covariance matrix, which is this matrix here, If you have a 2D Gaussian, it's going to be 2 by 2, and what the diagonals are the variance for each dimension, but then there's this term here, the covariance, and what that is there's some amount of the variance that is a function of both x and y, right? So this diagonal here is just the variance only in x, variance only in y, right? The independent x and y. But here, there might be a non-zero value. If there's 0 values here, it basically means that the variance in x is independent of the variance in y. But that's generally not going to be the case. Like most of the time, these covariances are going to have some value, which means that there's some relationship, there's some kind of interaction happening between the x and the y dimensions. So here, these are going to be 3D Gaussians. So this covariance matrix here is actually going to be 3 by 3. So you're going to have x, y, and z on the diagonal, and then y and x, y and z, x and z, and so on. All the difference covariance between this. But you can just kind of think of the 2D example of this and then project it into 3D with your brain if you're able to doing that. Okay, and spherical harmonic coefficients. Okay, this is spherical harmonics. These kind of pop up occasionally, and I'm just going to be real. I don't even fully fucking understand what they are, but they're going to be using them. Interleaved with adaptive density control steps where we occasionally remove 3D Gaussians during optimization. The term splatting isn't a standard term. Splatting has been used to refer to a technique where you splat or spread out data onto an image. Okay, so I think splatting doesn't have a specific formal definition. It's just literally the same mental image I have of just splatting something on a 2D surface, like you would splat some paint on a 2D surface. I guess here they're splatting a 3D Gaussian onto a 2D surface. Maybe one of you guys know what splatting is. The optimization procedure produces a reasonably compact, unstructured, and precise representation of the scene. 1 to 5 million Gaussians. That is, holy shit, 1 million Gaussians for every scene? That seems a lot. Okay, the third and final element is our real-time rendering that uses fast GPU sorting algorithms and is inspired by tile-based rasterization. So maybe they have their own custom CUDA kernel here. And with any kind of deep learning algorithm or any kind of deep learning or computer vision algorithm in general, there's the speed that you're going to get just from a theory standpoint of like, okay, how many times, what is the optimization process, how many iterations are you going to have to run, and so on. But then there's the actual speed. And what I mean by that is that there's certain algorithms that you can basically compile them into these CUDA kernels that are the code that actually runs on the GPU. And sometimes you can compile things in a way that makes them way faster, right? So sparse softmax, let me see if I can find this, sparse attention, something like that. There's this, bear with me for a second, not sparse attention. Fast attention. Yeah, here we go. So this is a little bit of a tangent here, but I think it proves my point. So you have the attention computation in a transformer, right? And the attention computation of a transformer, if you were to actually do the actual math, which is basically you're taking these value matrices, these query matrices, and these key matrices, if you were to actually do all of those steps in a GPU, this is how much time it would take, right? It would take about 20 milliseconds. You do a matrix multiplication, then you get rid of some things, then you put them through the softmax, then you do another mask, and then you do a matrix multiplication. But somebody figured out a way called flash attention that they were like, hey, wait a second. Every time I'm doing these matrix multiplies, I'm taking things out of the memory, I'm putting them into the memory, I'm taking them out of this memory that's closer to the matrix multiply processor and taking it out and putting it in. And they're like, wait a second, there's actually a much faster way of doing that where I can put things in intermediate memories and stuff like that. And look at this fused kernel, right, this CUDA kernel that implements the same thing as this attention mechanism here is significantly faster, right? And this is a huge speed up, right? So ultimately what I'm trying to get you guys to understand here is that there's a difference between kind of the theoretical, like, here's how complicated my algorithm is, and like sometimes some of those algorithms, if you actually write them and put them into a CUDA kernel and you're clever about that, you can have them run significantly faster. And with these type of 3D scene reconstruction papers, that's actually a huge part of whether or not you're going to achieve real-time rendering. So real-time rendering, it's not going to be about the assumptions that you make and like the optimization process. I feel like at the end of the day, like 80% of it is going to come down to the fact of like, is your algorithm capable of being put into a CUDA kernel that makes it drastically faster for some weird reason because of the way the memory works and the way that the matrix multiplies are done. So if they figured out a fast GPU implementation of their thing, that could be huge. Okay, thanks to our 3D Gaussian representation, we can perform anisotropic splattering that respects visibility ordering, thanks to the sorting and alpha blending, and enable fast, accurate backward pass by tracking the traversal of as many sorted splats as required. So it kind of sounds like they probably have something like that figured out. The introduction of anisotropic 3D Gaussians as a high-quality, unstructured representation of radiance fields. Optimization method of 3D Gaussian properties interleaved with adaptive density control that creates high-quality representations for captured scenes. Okay, so you have optimization method, you have the original 3D Gaussian prior, and then you have the fast differentiable rendering approach for the GPU. So those three together are why this method works, right? If they would have just stopped here, this paper would have just taken forever. It would have produced something that is, sure, it's high quality, but it takes like 10 hours to run on a GPU. No one cares about it, and it gets shuffled away and forgotten about. But they went that extra step of like, hey, let's actually try to make this fast on the GPU by implementing this in a really optimized CUDA kernel, and that's how they're able to get this state-of-the-art speed and state-of-the-art quality. All right, so that's what this paper is going to be about. So these are the three key contributions of this paper. Multi-view captures achieve equal or better quality than the previous best quality previous implicit radiance field approaches. We can also achieve training speeds and quality similar to the fastest method and provide the first real-time rendering with high quality for novel view synthesis. That could be huge. We'll see if NVIDIA has a paper for this technique in 6 months. Okay, related work. Unfortunately, I don't like these related work sections because they're just a citation fest, but let's see. Overview traditional reconstruction, then discuss point-based rendering and radiance field. Discussing their similarity, radiance fields are a vast area, so we focus only on directly related work. For a complete coverage, please see this excellent survey work. Okay, so you got some surveys. Survey papers are different from novel algorithm papers. So some papers are what's called survey papers, and those papers, they're not introducing any kind of new algorithm or new approach or new data set or new benchmark or anything like that. They're basically just saying, hey, there's 1,000 papers on this thing. We're just going to basically pick the best ones and tell you all the different techniques. These survey papers are generally like extremely long and can be very dry. So that's why I haven't really read a ton of them on stream. But I don't know, maybe we should start reading some survey papers. Traditional scene reconstruction and rendering. The first novel view synthesis approaches were based on light fields, first densely sampled. So we got some 1996 papers. And unstructured capture, 2001. Structure from motion in 2006. A collection of photos could be used to synthesize novel views. SFM uses a sparse point cloud during camera calibration, initially used for simple visualization. Multi-view stereo produced impressive full 3D reconstruction algorithms, 2007, 2013, 2008, 2018, 2021. All these methods reproject and blend the input images into the novel view camera and then use the geometry to guide the reprojection. So all of SFM and multi-view stereo are basically based around this idea of geometry, right? They're just looking at triangles and the position of things and the relative distance between things, and then using these triangles to get the camera positions and where other things in the scene would be. These methods produce excellent results in many cases, but typically cannot completely recover from unreconstructed regions or from over-reconstruction. When multi-view stereo generates inexistent geometry, recent neural rendering algorithms vastly reduce such artifacts and avoid the overwhelming cost of storing all input images on the GPU, outperforming these methods on most fronts. Okay. So that's where we're at with scene reconstruction and rendering. Traditional scene reconstruction and rendering. Neural rendering and radiance fields. So you got the deep learning techniques for novel view synthesis started around 2016. I think AlexNet was 2014. AlexNet was one of the first kind of computer vision deep learning successes. No, it's not even 2014, it's 2012. So it's 4 years after that. 2016 is when you started seeing these NeRFs. Used to estimate blending weights. Volumetric rendering representations for novel view synthesis were initiated by soft 3D. Deep learning techniques coupled with volumetric ray marching were subsequently proposed. I guess the first NeRF is maybe 2019, so this 2016 paper is more just deep learning, but CNNs used to estimate blending weights, so they were using it for different things. Building a continuously differentiable density field to represent geometry. This is the base, this is the prior that you use for a NeRF, right? So in a NeRF, you're saying, okay, there's some volume of space, and that volume of space has a density or an opacity, and that opacity is defined at every single point in space. And that's what a field of density is. And it's differentiable because it's continuous. Rendering using volumetric ray marching has significant costs due to the large number of samples required to query the volume. Large number of samples is, each of these little dots here is a sample, so you're going to need a lot of them. Introduced important sampling and positional encoding to improve quality, but used a large multi-layer perceptron, negatively affecting speed. The success of NeRF has resulted in an explosion of follow-up methods. We've read a bunch of them on this channel if you're interested, but maybe you shouldn't actually watch those videos, because if this technique is better, then maybe NeRFs just disappear and just become a footnote in the history. Current state-of-the-art in image quality for novel view synthesis is MIP NeRF 360. While the rendering quality is outstanding, training and rendering times remain extremely high. We are able to equal or in some cases surpass this quality while providing fast training and real-time rendering. Most recent methods have focused on faster training and or rendering by exploiting three design choices: use of spatial data structures to store neural features, different encodings, and MLP capacity. Different variants of space discretization, codebooks, encodings, hash tables. So people have been basically trying all kinds of different things on top of NeRFs to make them faster and or more high quality. Most notable of these methods is Instant NGP. This one actually has a very good NGP, very good GitHub repo. This is like a very, look at that, 13,000 stars on this GitHub repo, but it's basically a NeRF that is very fast, very high quality. Look at that. Look at this. Look at this. Look at this little Lego truck, which uses a hash grid and an occupancy grid to accelerate computation, and smaller multi-layer perceptron to represent density and appearance. And then Planoxels uses sparse voxel grid to interpolate the continuous density field. So you can see how hash grid and occupancy grid, and then a sparse voxel grid. So both Instant NGP and Planoxels are based on ideas that are looking at the actual voxel itself, the actual way that space is being represented, and saying, hey, is there a way that we could represent this space that's faster? So this paper is kind of similar in that way, right? Where it's just even a step further to that, but going back to the base assumption, I think is the way to make progress here. Damn, my brain is kind of fried. I don't know about you guys, but I feel like I'm not making sense. Interpolate a continuous density field and are able to forego neural networks altogether. Both rely on spherical harmonics, the former to represent directional effects directly, and the latter to encode its inputs to the color network. So the color network is the network that produces the color at a specific point. Both provide outstanding results. These methods can still struggle to represent empty space effectively, depending in part on the scene and capture type. Image quality is limited in large part by the choice of the structured grids, and rendering speed is hindered by the need to query many samples for a given ray marching step. The unstructured, explicit GPU-friendly 3D Gaussians. What? They're GPU-friendly. Achieve faster rendering speed and better quality. All right. So what are we going to go into here? Point-based rendering in Radiance Field. We're still in the related work section, so this is probably just going to be an explanation of what a nerf is. So we've seen that a million times at this point, but whatever. Let's just read their explanation of nerfs. Point-based methods efficiently render disconnected and unstructured geometry samples. Disconnected and unstructured geometry samples is a very fancy way of saying a point cloud. In its simplest form, a point sample rendering rasterizes an unstructured set of points with a fixed size, for which it may exploit natively supported point types of graphics APIs or parallel software rasterization on the GPU. Huh? While true to the underlying data, point sample rendering suffers from holes, causes aliasing, and is strictly discontinuous. So any technique that is based on these point clouds, you're going to get these holes, right? Because there's going to be parts of your scene that you can't get the correspondences right, therefore there is no points there, and therefore your reconstruction of that is not going to have is not going to know what's actually in that point in space. Causes aliasing and is strictly discontinuous. Seminal work on high-quality point-based rendering addresses these issues by splatting point primitives with an extent larger than a pixel. Okay, so here they're finally introducing the word splatting, and this is the idea of, okay, well, if you have a point cloud, right, which is a set of 3D points that represents something. Here you have a point cloud for a house, right? Maybe this was taken with a drone or something. Each of these points is infinitesimally small, right? So maybe what if you were to take all of those points and kind of just make them a little bit wider, right? Say that, okay, those points don't just represent the color of a very, very tiny, infinitesimally small point in 3D space. They represent the color and properties of like a little area of 3D space. Circular or elliptic discs, ellipsoids, or circles. Circles are kind of a cool look. If you guys have ever seen that, circles. Yeah, it's basically a point cloud, but you have each point you kind of spread it out. So now it has a radius, and it also has a normal direction. So here's a cube represented in circles. And you could compare that to a cube represented in meshes. Here's a mesh for a cube, right? In meshes, you have points, and then you have the normal vector kind of just happens because of the way that the points are connected together. But in a circle, each point itself has a normal vector. There has been recent interest in differentiable point-based rendering techniques. Points have been augmented with neural features and rendered using a CNN, resulting in fast or even real-time. However, they still depend on multi-view stereo for the initial geometry. Yeah. And as such, inherits its artifacts, aka whatever noise you're introducing with this multi-view stereo process, which is how you're creating this point cloud, you're not going to be able to get rid of that noise because the techniques are assuming that that multi-view stereo point cloud is ground truth when really it's not. Over or under reconstruction in hard cases such as featureless shiny areas. So what does it mean by featureless shiny areas or thin structures? So if we were trying to multi-view stereo let's go over here. So we have this house, right? Maybe that's not a good example. Maybe this is a good example. But let's say you were to take a picture with a cell phone of a white featureless wall, right? It would be very difficult to look at those different pictures and know where your camera was because there's just nothing in that white featureless wall to compare against, right? So the more kind of like textured and the more edges and little corners there are in a picture and a series of pictures, the easier it's going to be to use multi-view stereo to reconstruct that 3D scene, right? If you have something that has almost no features, it's going to be very difficult to reconstruct that. I'm trying to find like a good picture of this, but I really can't here. So normally that's not a huge problem because a lot of the things in real world have a ton of texture, but the fuck is that? That's kind of cool. Point-based alpha blending and NeRF-style volumetric rendering share essentially the same image formation model. Specifically, the color C is given by volumetric rendering along a ray. So the final color is you add up basically all the colors along every single point along this ray, accounting for the fact that some of them have high opacity. So you see here how the opacity here, they have it with the sigma here. And you can see how at some point the opacity peaks, which means that the color shouldn't account for the fact that what's behind it. So kind of as soon as you have one point that has a very high opacity, you kind of don't care about the samples after that. And actually, there's a bunch of NeRF papers that use this technique to make it faster, right? So like once you kind of know that you're seeing the surface of something, then you kind of don't need to sample further points along that ray. But here you have the final color is the sum of all the points from 1 to n, where n is the number of points along that ray. Each point has some opacity. Each point has some color. That's what this CI, that's what this opacity is. And this is the actual ray marching here. But you can basically just think of this image. Samples of density, transmittance, and color are taken along the ray with intervals delta I. This delta I is the distance between these points here and can be rewritten as this. With alpha I equals 1 minus exponent negative sigma I. So alpha I is basically just how far along you are. And it's based on the distance. See, it's a function of the distance and then also the opacity. A typical neural point-based approach computes the colors C of a pixel by blending n-order points overlapping the pixel. Okay. Ooh. So this is how you would do it in NeRF. This is ray marching, volumetric rendering with ray marching as you see it in NeRF. And then here, so that's equations 1 and 2. And then equation 3, this is going to be point-based rendering, where you're basically saying, okay, there's some pixel, and that pixel is going to have a bunch of points that are close to the pixel or overlapping the pixel. So think about a point cloud like this, and then you're saying, okay, well, what's going to be the color at this pixel here? So let me actually go and see which points are in some neighborhood of that pixel, and then I'll basically just do the average of that. And that's what you're seeing here. They're just blending points with some distance around the point. CI is the color of each point. Alpha I is given by evaluating the 2D Gaussian with covariance. Here you go. Here's a 2D Gaussian multiplied with a learned per point opacity. Okay, so there's an opacity for each point. We can clearly see that the image formation model is the same. However, the rendering algorithm is very different. Okay, I don't know what they mean by the image formation model is the same. I guess they're saying that for every pixel, you're basically kind of averaging a bunch of guesses of what that pixel would be. Maybe that's kind of what they mean by that. The rendering algorithm is very different. NeRFs are a continuous representation implicitly representing empty and occupied space. So what they mean by that is that you can evaluate this NeRF at any point in space, and that opacity is basically telling you whether or not it's empty space or it's occupied space, whether or not there's an object there. Expensive random sampling is required to find the samples. So you need to sample many points in order to get a guess for one pixel. I guess that's the image formation being the same in both this point-based approach and then the NeRF-based approach. With consequent noise and computational expense. In contrast, points are unstructured, discrete representations. So unstructured in that there's all points are independent. You can take a point cloud, which is a set of points, and they have some order to them, and you can shuffle them, and they have a new order, and it's the same exact point cloud. So there is no structure to the order of those points. Those points are just each their own little individual point. And it's discrete because there's some limited amount of points. That is flexible enough to allow creation, destruction, and displacement of geometry similar to NeRF. This is achieved by optimizing opacity and positions as shown in previous works, while avoiding the shortcomings of a full volumetric representation. So, okay, little comparison between NeRFs and these point-based approaches. Pulsar achieves fast sphere rasterization, which is inspired our tile-based and sorting renderer. Okay, so they're tile-based and sorting render, which we still don't know exactly what that is, but it's inspired actually on this 2021 work called Pulsar. So that's kind of cool. Given the analysis above, we want to maintain approximate conventional alpha blending on sorted splats to have the advantage of volumetric representations. What is an approximate conventional alpha blending? A rasterization respects visibility order in contrast to their order-independent method. Okay, so visibility order is things that are closer to you are going to be more visible than things that are far away. So if you have something ahead of you that is semi-transparent, you're going to pay attention to that before you pay attention to the thing in the back, right? So and the NeRF accounts for that as well, right? There's not just the notion of the opacity, but there's also the notion of the order. So you're going to see through the points here. And even if this last point has a very high opacity, because it's the last point, it's probably not going to have much of a contribution. So it's not just the individual see-throughness, it's also the order that you're getting because you know where you're trying to render it from. In addition, we backpropagate gradients on all splats in a pixel and rasterize anisotropic splats. I'm going to fucking look up anisotropic here. Anisotropic. What does it mean? Come here. Anisotropic. What does it mean? Okay, so it comes from the Greek word an, meaning not, and then iso, meaning the same. So not the same. Property being directionally dependent. Okay, so basically, in a NeRF, this little multi-layer perceptron here knows what the direction of the ray is. So it's direction dependent. If you're looking at something from this angle, it's different than if you're looking at it from this angle. So the NeRF, it has to account for that, right? The representation has to account for the fact that, okay, where are you viewing this from? These elements all contribute to the high visual quality of our results. In addition, previous methods mentioned above also use CNNs for rendering, which result in temporal instability. Temporal. There's no time here. Nonetheless, the rendering speed of Pulsar and ADOP serve as a motivation to develop our fast rendering solution. While focusing on specular effects, the diffuse point-based rendering track of neural point Caustics, overcome this temporal instability by using a multi-layer perceptron, but still require MVS geometry as an input. The most recent methods in this category also do not require MVS and also use SH for directions. However, it can only handle scenes of one object and needs masks for initializations. So yeah, you definitely don't want that. You definitely don't want a technique where you have to say, here's a picture of my scene, and then here's a mask of everything that's background, everything that's foreground. While fast for small resolutions and low point clouds, it is unclear how it can scale to scenes of typical datasets. We use 3D Gaussians for a more flexible scene representation, avoiding the need for MVS geometry and achieving real-time rendering thanks to our tile-based rendering algorithm. So it does seem like their tile-based rendering algorithm is really just coming from these two previous works here, Pulsar and ADOP, which had some kind of fast rendering solution, which is also tile-based. So this is maybe a little bit less original than they're making it seem. It seems like it's more just inspired by a previous approach. Catacaustics is an awesome word. Yeah, caustics I think is the interaction of lights with like glass, I'm pretty sure. Yeah, so this type of stuff. So you know who actually is really good at this? If you guys have ever heard of 2-minute papers, this is, I heavily recommend this YouTube channel, but this is like a guy who he basically does what I do. He like reviews papers, but he does it in little tiny, he basically does these like super short summaries. But the guy who owns this channel, he actually comes from a computer graphics background. So occasionally some of the papers that he talks about here are these kind of papers where they're trying to solve these caustic problems. And I remember he has a couple, I'm not going to be able to find them just right off the bat, but there's a lot of super fancy kind of work that people have done for decades about old school kind of physics-based rendering, right? Where you're actually like looking at the way that light actually interacts with a piece of glass in order to create this kind of caustic effects that you would get maybe at the bottom of a pool here, or like something like this when you see it through a glass. And like this shit is like very complicated, right? Because the way that light is interacting with a glass object, it's like you could even have to account for like quantum effects in there, right? Because the way that light bounces, and it's just incredibly complicated. So hats off to the people that actually understand that garbage. Okay, let's get back to here. They employ point pruning and declass densification techniques. So point pruning is just when you have your point cloud and then you basically get rid of points that are maybe just spurious or weird. Densification, adding more points during optimization, but use volumetric ray marching and cannot achieve real-time display rates. The domain of human performance capture, 3D Gaussians have been used to represent captured human bodies. Okay, so 3D Gaussians might not even be original to this paper. Obviously, it makes sense that 3D Gaussian is a very kind of basic primitive, so people have probably come up with 3D Gaussians as a prior for decades. I'm sure there's even earlier papers from like the 70s or 80s that have something that's using 3D Gaussians. More recently, they have been used with volumetric ray marching for vision tasks. Neural volumetric primitives have been proposed in a similar context. While these methods inspired the choice of 3D Gaussians, they focus on the specific case of reconstructing and rendering single isolated objects, resulting in scenes with small depth complexity. In contrast, our optimization of anisotropic covariance, our interleaved optimization and density control, and efficient depth sorting for rendering allow us to handle complete complex scenes, including background both indoor and outdoor with large depth complexity. So there isn't kind of a formal definition for large depth complexity or complete scenes. Like those are all just kind of a little like subjective words, but I think largely what they're trying to say is that we're not just going to have some results like these NERF papers where there's just one thing in the middle of the thing and everything else is background and it's just this magical object hovering in 3D space. They're going to be doing more complicated scenes such as this. I would call this a complicated scene because there's a lot of different things here. You have the background itself changes, but then you have very complicated interactions such as the lighting on this TV, right? Like that is some next level shit. And not only that, but actually if you look here, there's the reflection of the TV contains the table, which itself is reflecting something. So I would call that a complete complex scene. Overview. Okay, so now we've finished the related work section where they kind of showed us previous papers, previous research that people have done that is similar to this. And now we're going to go into the actual thing that they're doing in this paper. So the input to our method is a set of images of a static scene. And right off the bat, that makes you kind of sad, right? Because one of the things that none of these papers, including this paper and every single NERF paper, address is the fact that these are static scenes, right? Ideally, we want to get to the point where these are time-varying scenes, right? It's not just a single static thing. It's like a video, right? I want to get to a point where we have NERF videos. You have like a NERF video that you could put on a VR headset and then explore that video itself, right? So the fact that we're still just dealing with these static scenes is a little bit annoying. Combined with corresponding cameras calibrated by SFM, so This is also unfortunate because it means that you're using the SFM to give you the camera positions, which means that you're only as good as the SFM, which produces a sparse point cloud as a side effect. From these points, we create a set of 3D Gaussians. These Gaussians are going to be defined by a position, which is going to be 3 numbers, a covariance matrix, which is going to be a 3x3 matrix, and then an opacity alpha that allows for a very flexible optimization regime. This results in a reasonably compact representation of the 3D scene. Reasonably compact representation of the 3D scene. And it's also, you're going to be able to kind of trade off the quality and the speed, right? Because you're going to have to pick how many of these 3D Gaussians you have. So if you pick 10 Gaussians, it's going to be very fast, but probably complete shit. But if you pick 10 million Gaussians, it's going to be very, very good, but very slow. So having a variable like that, a hyperparameter that you can choose that allows you to kind of trade off between fast and cheap and then high quality and slow is generally very useful. In part because highly anisotropic volumetric splats can be used to represent fine structures compactly. Representing fine structures. So fine structure might be like a post in some kind of bed or something like that. Something that's very thin and long, or something that's very small. The directional appearance component, color, of the radiance field is represented via spherical harmonics. Okay, so here you can see that each of these 3D Gaussians has an opacity, and it has a position and a covariance, which is just kind of the spread, but it doesn't have a color. So where is the color going to be stored? And the color is going to be stored in these spherical harmonics, following standard practice. Our algorithm proceeds to create a radiance field representation via a sequence of optimization steps of 3D Gaussian parameters, interleaved with operations for adaptive control of the Gaussian density. The key to our efficiency is our method is our tile-based rendering that allows alpha blending of anisotropic splats representing visibility order thanks to fast sorting. Okay, so this fast sorting, which they're doing on the GPU, is going to tell you which Gaussian is in front of the other Gaussian, which is going to be important, right? Because for the nerf, you start from saying, I have this pixel means that I have this ray, and that ray means that I have samples along that ray. So you kind of start from the pixel, then the ray, then the points. And you have to then sample for each of those points. But here, they're going to have a bunch of Gaussians, but those Gaussians, you're not going to know the order of those Gaussians from a specific view that you haven't looked at before. So you're going to have to sort these Gaussians. And it seems like they can do that sorting on the GPU quickly. Out fast renderer, this is probably a typo. This probably says R fast rasterizer. That's what it probably should be. R fast rasterizer also includes a fast backwards pass by tracking accumulated alpha values without a limit on the number of Gaussians that can receive gradients. Okay, interesting. So in a nerf, there's some hyperparameter, which is how many samples am I taking along this ray. But it sounds like with this technique, you're not limited to that specific number of sampled points. You can basically, if you have 1 million Gaussians and all 1 million of those Gaussians are in this specific order for this one specific novel view, you could push gradients into every single one of those Gaussians. Of course, that's probably going to be not ideal, right? Generally, if you're going to do some kind of training process like this, knowing the exact number of Gaussians so that you can basically fit it perfectly in your GPU memory, there's an advantage to that. So I wonder if they actually have a hard-coded limit on the number of Gaussians per backward pass. Differentiable 3D Gaussians. Our goal is to optimize a scene representation that allows high-quality novel view synthesis starting from a sparse set of SFM points. We need a primitive that inherits the properties of a differentiable volumetric representations while at the same time being unstructured and explicit to allow very fast rendering. We choose 3D Gaussians, which are differentiable and can be easily projected into 2D splats. So you can take a 3D Gaussian and then splat it. So kind of similar how here we have a 2D Gaussian and we're splatting it into 1D. So you can see here this is a one-dimensional splat of a 2D Gaussian. So they're going to be doing the same thing, except they're going to be doing a two-dimensional splat of a 3D Gaussian, which looks like this, right? These little Gaussians. A representation of similarities to previous methods that use 2D points and assume each point is a small planar circle with a normal. This is a circle. So we were actually just looking at that. Where is our circles? Here we go. Little circles. Look at these. Look at these circles. Approximating a surface with a bunch of circles. Given the extreme sparsity of SFM points, it is very hard to estimate normals. Yeah, you can't just connect the points and assume that the resulting triangle gives you an estimate of the normal. Similarly, optimizing very noisy normals from such an estimation would be very challenging. Instead, we model the geometry as a set of 3D Gaussians that do not require normals. Our Gaussians are defined by a full 3D covariance matrix defined in world space. So world space just means that there's some global origin, and you're basically saying there's some 0, 0, 0 point, and then all of these Gaussians, the position of them, the covariance, every number is based on that origin, that 0, 0, 0 point. Centered at a point mean mu. So the point mean mu is going to be a three-dimensional vector, and then your 3D covariance is going to be 6 numbers. So here you have a Gaussian, here you have the covariance. What is x? X is just any point, I guess. Gaussian is multiplied by alpha in our blending process. Alpha is kind of the opacity equivalent. We need to reproject our Gaussians into 2D for rendering. Demonstrate how to do this projection to image space. Given a viewing transformation W, the covariance matrix E sigma prime in camera coordinates is given as follows. J is the Jacobian of the affine approximation of the projective transformation. Okay, so Jacobians are basically a matrix that has the derivative of all the terms in a thing for every different thing in the thing. Let's see if there's a better definition of that. Jacobian determinant of... No, that's not what I want. I just want... Yeah, basically this. So whenever you think of a Jacobian, think of this. It's basically df1, dx1, df1, dxn, df2, df2, dx2, df2. So you see it's basically just like the partial derivative of the function with respect to all the different things. So here, the Jacobian is going to have a term for x, and a term for y, and a term for z, and so on. And here your viewing transformation w, that's going to be a... let me see if I can give you a good picture to that. Homology. No. Affine transformation computer vision. Yeah, so an affine transformation is this matrix here, and it can take a 2D image and then basically warp it like this. So you see, there's a matrix that represents this warp. So here, for example, in this little thing, their affine transformation has this R, which is a rotation matrix, and then B, which is a translation, right? So you can have different types of transformations represented in this affine transformation. So this viewing transformation is basically a transformation that takes that 3D Gaussian and then gives you that 2D slice kind of view from whatever the view direction is. And the view direction is just going to be like, where are you actually trying to get this 2D picture from? So here in this NERF example, right, the NERF is the 3D volume. You want an actual 2D image that there's some transformation to get this 2D flat plane to the Gaussian that would be defined there in this case. Okay. Also show that if we skip the third row and column of that, we obtain a 2D 2x2 variance matrix with the same structure and property. Okay, this is kind of sketch. So they skip the third row and column of the covariance matrix, which means that the covariance matrix here is a 3x3 because it's a 3D Gaussian. But here they're saying if you skip the last row and column, then you get a 2x2, but that's just going to be the X and Y. Huh. That's kind of weird. Like, aren't you going to lose information if you do that? Because it's going to be the X and Y, but the X and Y specifically in the world space X and Y, which is going to be different than the X and Y in your view coordinate frame. Seems a little sketchy. I don't know what's going on there. An obvious approach would be to directly optimize the covariance matrix to obtain 3D Gaussians that represent the radiance field. However, covariance matrices have physical meaning only when they are positive semi-definite. Yeah, so you can't have negative variance. So any covariance matrix, let's go here, right? These values here can't be negative. That doesn't make any sense to have a negative variance. So you know at least the diagonals are going to be positive, and then there's also some requirement on these covariant terms as well. The positive definite requirement, which is like some specific. What is the positive definite? Where is it? All definite matrix. Here you go. M is positive definite if for all points X, in this case they're going to be 3D points, the transpose of X times MX is greater than or equal to 0. So that's the formal definition of positive definite. And then you have here a bunch of other ones. Positive semi-definite, negative semi-definite. But the reason that this covariance matrix is positive semi-definite is because it's representing the variance of a Gaussian, which has specific properties like the fact that you can't have a negative variance, which means that this matrix has to be positive semi-definite. For optimization of all of our parameters, we use gradient descent. Okay, that's basically the same technique that everybody has. Cannot be easily constrained to produce such valid matrices. Okay, so they're saying, okay, well, if we're trying to use gradient descent to find this covariant matrix, because at the end of the day, we want to basically figure out this magical set of 3D Gaussians that have these properties that represent this scene, we're going to basically use gradient descent to get the position of these Gaussians, to get the covariance matrix of these Gaussians, to get the opacity of these Gaussians, and to get the coefficients of the spherical harmonics, which end up being the color. So we're going to have to get all of those, and eventually we want to basically learn those using gradient descent. However, if we just start taking little incremental steps, this covariant matrix might just be nonsense, right? Because it has to be this positive semi-definite. It has this constraint because it's a covariance matrix. So how are we going to use gradient descent to get valid covariance matrices? All right. So we opted for a more intuitive yet equivalently expressive representation. The covariance matrix of a 3D Gaussian is analogous to describing the configuration of an ellipsoid. Okay, so a 3D Gaussian is an ellipsoid. I guess that kind of makes sense. That's in all their pictures here, they're kind of showing a Gaussian as a little ellipsoid. Here they're 2D ellipsoids, but obviously in 3D they're going to be a 3D ellipsoid. So you have some scaling matrix S and some rotation matrix S, R. You can find the corresponding covariance. Okay, so they're basically saying the covariance matrix of a 3D Gaussian, which we have here. Where is it? Where's our Gaussian? Oh no, Caustics? Definite matrix? I think it's because we got rid of this. Yeah, so we have our 2D Gaussian, and then the 2D Gaussian has some spread, right? It has a variance. But another way to think of that spread or that variance is basically pretend it's a circle, pretend it's a little ellipsoid, and then instead of the variance, what we're defining is basically the radius of this ellipsoid. And the same way that there's going to be some variance in X and some variance in Y and some variance in Z, now you're basically going to say, okay, there's an ellipsoid, and that ellipsoid is going to have some radius in X, some radius in Y, and some radius in Z. Okay, so if we have an ellipsoid, then we can just say, okay, well, all ellipsoids are this unit ellipsoid that's scaled and then rotated. So they're going from, we want to get a covariance matrix for a 3D Gaussian that's hard to do because there's specific requirements on covariance matrices. So let us instead pretend that these 3D Gaussians are these little ellipsoids, and we're going to take, and we're instead going to find the scaling, which is kind of like the stretching, and then the rotation of that ellipsoid, and then we're going to pretend that that matrix is the covariance. Reminds me of SVD, singular value decomposition. Yes, I kind of see what you're saying. To allow independent optimization of both factors, we store them separately. A 3D vector S for scaling and a quaternion Q. Yes, dude. I love quaternions, dude. Quaternions are my favorite. I think rotation matrices are also popular, but there's Euler angles, there's rotation matrices, and then there's quaternions. And I feel like quaternions are the best way to represent rotations. And you can convert from quaternions to rotation matrices and back to quaternions. So these can be trivially converted to the respective matrices and combined, making sure to normalize Q to obtain a valid unit quaternion. Okay, so here, obviously, this S is going to be a 3D vector, and you can't multiply a 3D vector with a quaternion, which is 4 numbers. So anytime they're going to get these covariance matrices, they're going to convert these quaternions into these rotation matrices, so that the rotation matrix, which is going to be 3 by 3, the dimensions match with this scaling vector, and thus you can get the final covariance matrix, which is going to be a 3 by 3. To avoid significant overhead due to automatic differentiation during training, we derive the gradients for all parameters explicitly. What does that mean for that? Details of the exact are in Appendix A. Details of gradient. Recall that sigma over sigma prime are in the world and view space. Okay, so sigma prime here, which is the covariance matrix, that's the 2D version of it, is inside the view space. So view space is this image here, versus world space is the actual 3D world space. Q is the rotation, S is the scaling, Q is the quaternion. W is the viewing transformation, and J is the Jacobian of the affine approximation of the projective transformation. We apply the chain rule to find the derivatives. Okay, so you want to find what is the partial derivative of this covariance matrix with respect to this scaling. That's equal to the partial derivative of the covariance matrix with respect to this other covariance matrix. So this is just the chain rule here. More chain rule. Using U equals JW and sigma prime being the symmetric upper left 2 by 2 matrix of, so this is where they're only taking the top part, denoting matrix elements with subscripts, we can find their partial derivatives. Okay, so why are you doing the chain rule here? It's because you can't actually get the you can't actually get this derivative, but you can get this derivative, right? So anytime you're using the chain rule, it's because you can't find what you really want, so you break it up into more things, and then you can get each of those things individually. So here they're saying, okay, well, we can actually get what this is, and then we can get what this is. So if we can get what this is and we can get what this is, then we can get what we really want, which is this, right? We seek derivatives that since sigma is RS S transpose R transpose, we can compute M equals RS and then rewrite sigma equals MM. Okay, so they're combining the scaling and the rotation into one matrix M, and then that allows them to redefine DEDS, so they're going to further break this down into DEDM, DMDS, so another chain rule. Since the covariance matrix and its gradient is symmetric, the shared first part is compactly found by this. Is the covariance symmetric? I guess it is. For scaling, we further have that. To derive gradients for rotation, we recall the conversion from a unit quaternion with a real part and imaginary part to the rotation matrix R. So this is just how you convert from a quaternion. Quaternions have 4 parts. They have R, I, J, and K. And then here are how you get each of the values for a 3 by 3 rotation matrix if you have the 4 numbers of a quaternion. We find the following gradients for the following components. Okay, so you chain rule again, and then you now can get the partial derivative with respect to each of the quaternion elements. which is this. All right. Pretty cool story. This representation of anisotropic covariance suitable for optimization allows us to optimize 3D Gaussians to adapt to the geometry of different shapes in captured scenes, resulting in a fairly compact representation. They keep saying compact here, but it's not actually compact, right? Because if you had 10 million Gaussians, that would not be compact. The compactness is going to be how many Gaussians are you using. Optimization with adaptive density control. Adaptive density control, adapting the amount of Gaussians that you have based on where in 3D space. So it makes sense that in certain parts of 3D space, you're going to have more Gaussians. In certain parts of 3D space, you're going to have less Gaussians, right? So there's going to be some, it's going to be scene dependent too. So some scenes maybe have stuff in the corners, and you're going to need 3D Gaussians in those corners to represent that stuff. Core of our approach is the optimization step, which creates a dense set of 3D Gaussians accurately representing the scene for free view synthesis. In addition to positions P, alpha, and covariance, we also optimize the spherical harmonic coefficients representing the color of each Gaussian. So you're only going to have one color for the Gaussian, which means that these Gaussians can't be big, right? They're going to have to be very small Gaussians. Like, here it's making it seem like these Gaussians are like big, right? But they're not. That each Gaussian has the same alpha and it has the same color. So really these Gaussians are going to be very tiny. Really this is almost more similar to a circle. It's almost like a 3D circle is basically what this is. To correctly capture the view-dependent appearance of the scene. Boo-boo. Boo-boo wants to be on camera. The optimization of these parameters is interleaved with steps that control the density of Gaussians to better represent the scene. Okay, let's actually read, or actually let's look at this optimization first, and then we'll look at this figure, because I think this figure just describes what this text is going to do here. The optimization is based on successive iterations of rendering and then comparing the resulting image to the training views in the captured dataset. Okay, so basically you're going to optimize, get a final picture, compare the final picture to the ground truth picture, get a loss, push that loss, and then re-optimize. So there's kind of this back and forth process. Inevitably, geometry may be incorrectly placed due to the ambiguities of 3D to 2D projection. Our optimization thus needs to be able to create geometry and also destroy or move geometry if it has been incorrectly positioned. Okay, so basically this is kind of interesting. You have some set of Gaussians, and here I would have thought that you have the same set of Gaussians and then you're just moving them around. But here the word create and destroy means that they're going to be adding new Gaussians or potentially removing Gaussians over the course of this optimization process. I think this is annoying because it means that there's a different amount of Gaussians. It's like, generally, when you're doing anything with a computer, if you know the exact amount of things that you're going to have the entire time, it's a lot faster than if the amount of things is changing over time. So destroying and creating Gaussians seems like it might be a bad idea. The quality of these parameters is critical for the compactness of the representation, since large homogeneous areas can be captured with a small number of large anisotropic Gaussians. Yeah, so if you have one big white surface, you can pretty much just represent it as one big Gaussian that has very large variances in some dimensions and very small variances in a different dimension. We use SGD for optimization, taking full advantage of the standard GPU accelerated frameworks and the ability to add custom CUDA kernels. Custom CUDA kernels for some operations. Following recent best practice, our fast rasterization is critical to the efficiency of our optimization, since it's the main computational bottleneck. So kind of what we were talking about at the beginning of this paper, when these type of optimization problems, if you can frame them in such a way that the bottlenecks are implemented in extremely fast code, it makes a huge difference. We use a sigmoid activation function for alpha. Of course, your see-throughness, your opacity, your alpha blending or whatever, you're going to need to have that in a 0 to 1 range. Hence, you're going to use the sigmoid in order to do that. Obtain smooth gradients and an exponential activation function for the scale of the covariance for similar reasons. We estimate the initial covariance reason as an isotropic Gaussian with axes equal to the mean of the distance to the closest 3 points. So these points are the structure for motion points. So they're initializing the Gaussians from the point cloud that is sparse that you're getting from the structure from motion, and you need to have your initial guess needs to not just be the center or the mean of the Gaussian, but also the variance of the Gaussian, the variance in each of the three axes, x, y, and z. So basically, the distance of the different points in the structure from motion guess is gonna be the starting point for the variance of these Gaussian blobs. We use a standard exponential decay scheduling technique similar to planoxels, but for positions only. The loss function is combined with a DSSIM. So SSIM is a structural similarity index. It's a way of measuring whether two images are similar. I actually don't really like it, but it's an older one at this point. Yeah, here we go. It's actually kind of complicated because you're looking at images and you're saying, okay, the SSIM between two images, an image X and an image Y, is the combination of a bunch of weird shit, including luminance, contrast, and structure. So you're trying to say two images are similar. Here's a better example of it. But how similar is this image to this image, this image to this image, this image to that image? SSIM will give you a number, which tells you how similar they are, but that number accounts for potentially different contrast, different placing. But there's a lot, like this is some hard-coded human design thing. So there's definitely nothing sacred about this. So here's an original image of Einstein, and then here's a couple different variants of that image of Einstein, and then here they're showing you how, even though the PSNR is the same for these images, the SSIM between these is different. So this is the most similar with an SSIM of 0.98, and this is the least similar with an SSIM of 0.69. So their loss function here has this SSIM because they want the resulting image to match the training views in the captured data set, right? So at the end of the day, they want their little Gaussians, when they project them into 2D and add them all together with this alpha, they want that resulting image to be as similar as possible to the actual ground truth image. And that's where this SSIM loss is going to come in. But they also have this L1 loss, which is just the difference of every single pixel. We use lambda equals 0.2 in all of our tests. So this is just some hyperparameter that is basically blue color for the hyperparameter. But L1 loss for all the pixels. So you're taking pixel in reconstructed image, pixel in ground truth image. What's the difference? Add that to the pixel 2 in reconstructed image, pixel in ground truth image. What's the difference? So this is kind of a very primitive loss, to be honest. These are kind of simple losses here, and then your hyperparameter just trades off between both of them. Okay. Maybe we can look at this figure 2 now. Let's look at this figure 2. Optimization starts with the sparse structure from motion point clouds and creates a set of 3D Gaussians. So you're starting from this sparse point cloud, so you see how there's a sparse number of points here, and creates a set of 3D Gaussians. Here's your set of 3D Gaussians, and it kind of looks like you're starting from each of these points. We optimize and adaptively control the density of this set of Gaussians. Okay, so first thing you do is you project them into 2D. Once you project them into 2D, which is this transformation here, right? This viewing transformation and then this projective transformation, you can get a 2D version of that, which is the image. That 2D version you differentiably tile rasterize. This is the thing that they are doing quickly in the GPU. That gives you the image. Once you have the image, you can compare that to the ground truth image, and you use this loss here, right? L1 plus L2, you get that loss. You chain rule all the way back. That gives you the gradients, and the gradients you can see how they're flowing all the way back. So they're flowing through this differentiable tile raster, and that's why differentiable is key here, right? If this tile rasterizer was not differentiable, you wouldn't be able to flow the gradient through it like this, right? So the fact that it's differentiable is critical because it means you can chain rule all the way back, right? So you chain rule back here into this adaptive density control, you chain rule back here into this projection, and then you chain rule back into the 3D Gaussians themselves. So based on the loss, this reconstruction loss of your image here, you're changing the values of these 3D Gaussians, and the values are basically their positions, their covariances, their color, and their alpha. All right, and that's basically it. We use our fast tile-based renderer, allowing competitive training times to state-of-the-art fast radiance fields. Once trained, our renderer allows real-time navigation for a wide variety of scenes. So if you can real-time render based on a novel view, this is the novel view here, so the camera, this means that I'm asking my 3D representation to say, okay, well, what is the view from this camera? And what is the view from this camera? And what is the view from this camera? And what is the view from this camera? So like, if that process is fast, right, if you can very quickly say, okay, I already have a set of 3D Gaussians that are pretty good, and you ask, give me a camera position, I'll project it into that, I'll quickly rasterize it with this tile rasterizer, and I'll give you the image. If I can do that at like 30 frames per second, that means I can fly around in my scene at 30 frames per second, which means I can navigate through that scene. Okay. 5.2, still in the section 5 here. So this is still what they're doing. We start with an initial set of sparse points, then apply our method to adaptively control the number of Gaussians and their density over unit volume. Okay, so this is the adaptive density control, allowing us to go from an initial sparse set to a denser set that better represents the scene and with correct parameters. After optimization warm-up, we densify every 100 iterations. So every 100 iterations, you're removing a bunch of Gaussians and then adding a bunch of new Gaussians. We remove any Gaussians that are essentially transparent. Okay, so over time, right, you're using this gradient signal coming from this image reconstruction loss, and you're pushing that into the parameters of these 3D Gaussians. And some of the parameters of those 3D Gaussians are this alpha, right, which is basically how see-through it is, opacity here. So if you have some Gaussians here that are basically entirely see-through, then they're probably not doing very much, and we could probably just get rid of them. So that's what they're going to say. Every 100 iterations, let's go through all the Gaussians that we have, and then we're just going to get rid of the ones that are basically transparent, which means that they're the ones that over time the gradient descent was saying, make that one more see-through because it keeps fucking us up. Make that one more see-through. Make that one more see-through. And then over time, they're like, okay, well, this one seems to be so see-through that it's not really doing anything at this point. Let's just get rid of it. It's kind of like a pruning. Our adaptive control of Gaussians needs to populate empty areas. Okay. It focuses on regions with missing geometric features, but also in regions where Gaussians cover large areas. Okay, so they removed Gaussians based on the opacity or transparency. And now they're going to add Gaussians in areas that don't have a lot of Gaussians, or maybe just have one Gaussian that is kind of super big and super spread out. We observe that both have large view space positional. Intuitively, this is because they correspond to regions that are not well reconstructed, and the optimization tries to move the Gaussians to correct this. Interesting. Okay, so if these gradients that you're pushing are telling you to, hey, this Gaussian over here, move it 50 feet in that way, right? Then you're probably like, something's going on here because it's telling me to move this Gaussian a large amount. So there's probably not a lot of information here. So why don't I add another Gaussian in that area in order to basically better reconstruct that area? Since both cases are good candidates, we densify the Gaussians with an average magnitude above some threshold position. So you have a couple different. This is not necessarily good because you have basically these hard-coded thresholds here. So you have a threshold T-pose, you have a threshold alpha as well. for next details. For small Gaussians that are in under reconstructed, we need to cover the new geometry that must be created, preferably to clone the Gaussian by simply creating a copy of the same size and moving it in the direction of the positional argument. Okay, so in order to add Gaussians, they're not adding Gaussians that are entirely new and from scratch in the way that they would when they initialize the scene. They're basically cloning these Gaussians. So they're basically going to, if you have a Gaussian that is getting told to move a lot by the gradient, then clone it and then just move the clone. On the other hand, large Gaussians in regions with high variance need to be split into smaller Gaussians. Okay, so you can split a large Gaussian. We replace such Gaussians by 2 new ones and divide their scale by a factor of 1.6, another hard-coded number, which we determined experimentally. So this optimization process has 3 different hyperparameters here that are all just hard-coded. You have this position threshold, you have this transparency threshold, and you have this kind of scaling divide factor. That's not good. That means that you have to explore a larger, the more hyperparameters you have, the harder it is to find the magical set of them that produces the best results. In the first case, we detect and treat the need for increasing both the total volume of the system and the number of Gaussians, while the second case, we conserve the total volume but increase the number of Gaussians. Similar to the other volumetric representations, our optimization can get stuck with floaters close to the input camera. Interesting. Okay, so you can get a situation where you have just a Gaussian that's very close to the camera that kind of tries to control everything, so you maybe have to have some additional regularization to penalize Gaussians from kind of like drifting towards the camera. An effective way to moderate the increase in the number of Gaussians is to set the alpha value close to 0 every n equals 3,000 iterations. Okay, so more hard-coded hyperparameters here. And this is interesting because it's like they're having to deal with the fact that you have these Gaussians, right? And the Gaussians have a transparency, and then they also have a color. So you could see how the gradient optimization, if you're trying to, say, match this black thing, you could be like, okay, well, make this Gaussian a little bit bigger, or make the Gaussian a little bit less transparent, or make the Gaussian a little bit closer, right? So you could see how there's like, you could get to the same, or you could take gradient steps in different directions that are both making your loss better, right? So if you have like a Gaussian that's representing this object, you could make the Gaussian bigger by increasing the variance, or you could make it come closer to the camera. And by coming closer to the camera, it's kind of effectively bigger, right? So it's kind of a tricky optimization process. The optimization then increases the alpha for the Gaussians. To remove Gaussians with alpha less than that, Gaussians may shrink or grow and considerably overlap with others. But we periodically remove Gaussians that are very large in world space and those with a big footprint in view space. This strategy results in overall good control over the number of Gaussians. So these are regularization of the Gaussians. You don't want them to get too big, you don't want them to get too close, and so on. The Gaussians in our model remain primitives in Euclidean space at all times, unlike other methods. We do not require space compaction, warping, or projection strategies for distant or large Gaussians. Our adaptive Gaussian densification scheme. Under reconstruction. So let's say you have a Gaussian here that's getting told to move a lot. You clone it, and then you move just the clone. So this is the part that they were saying here, cloning the Gaussians. And then over reconstruction, so maybe your Gaussian is too big, so here you have a huge Gaussian. We're going to split it, and that's going to be the division with this scale factor here. Fast differentiable rasterizer. Okay, so that's how they're optimizing this set of Gaussians over time to eventually approximate this scene, and the losses that they're using are actually relatively simple losses that are just image reconstruction losses. And they're projecting that all the way back and changing this set of Gaussians to eventually mimic the real scene. But now, kind of the second kind of magical piece of this paper is, okay, well, this is only going to be useful if you have a way to turn those 3D Gaussians into a 2D image in a very fast efficient way. And that's what they're going to show us here. They're fast differentiable rasterizer for Gaussians. Our goals are to have fast overall rendering and fast sorting to allow approximate alpha blending, including for anisotropic splats, and to avoid hard limits on the number of splats that can receive gradients. So if you have different alpha values, that's going to tell you, okay, well, if this is partially see-through and if this is partially see-through, which one is in front of the other one, right? So the order matters when you're doing this alpha blending. Ooh. We design a tile-based rasterizer for Gaussian splats inspired by recent software rasterization approaches that pre-sort the primitives for an entire image at a time, avoiding the expense of sorting per pixel. Okay, so this is... If you were going through your 2D image pixel by pixel, you would have to sort the Gaussians for every single pixel, and that would be very slow. So they're going to pre-sort the Gaussians for the entire image and then do the alpha blending at each pixel. Our fast rasterizer allows efficient backpropagation over an arbitrary number of blended Gaussians with low additional memory consumption, requiring only a constant overhead per pixel. Our rasterization pipeline is fully differentiable and, given the projection of 2D, can rasterize anisotropic splats similar to 2D splatting. And the fully differentiable is key there because you need to be able to push the gradients back through that. Our method starts by splitting the screen into 16 by 16 tiles. So interesting that the 16 by 16, that's the exact size of tiles that are, or patches that are often used in vision transformers. Everybody loves the numbers 2, 4, 8, 16, 32, 64. Those are always very popular numbers. And then proceed to cull. Let me just highlight this in blue to make sure my highlights are correct. And then proceed to cull the 3D Gaussians against the view frustum. Frustum is the point here. Camera geometry pinhole model. The frustum is the point in a triangle. See if I can find frustum. Is there any picture here? Camera center. I think this might be the frustum right here. We only keep Gaussians with a 99% confidence interval intersecting the view frustum. Additionally, we use a guard band to trivially reject Gaussians at extreme positions. Okay, so you have a view, right? You have a specific 2D view, and then you have this kind of set of 3D Gaussians. So first they're going to use guard banding, which basically says, okay, if the 3D Gaussian is all the way over here, I probably don't give a shit about it. It's not going to appear in my image, so therefore let me not even use it for this sorting. Those are the means, since computing their projected 2D covariance would be unstable. We then initiate each Gaussian according to the number of tiles they overlap and assign each instance a key that combines view space depth and tile ID. Okay, so they're breaking up this view into these tiles, and then they're saying which Gaussians are visible from which tile. We then sort the Gaussians based on these keys using a single fast GPU radix sort. Okay, so basically the entire reason this is fast is because GPUs can do radix sorts. Let's ask. Eli 5 GPU radix sort. All right, let's break this down. Imagine you're trying to sort a deck of playing cards and you want to do it efficiently. The approach is the radix sort. To explain a GPU radix sort, we'll start with the basics of a radix sort. Numbers have multiple positions, like ones, tens, hundreds. Instead of trying to sort all the numbers of 1, radix sort breaks it down by sorting numbers based on positions. It'll first sort based on the 1s, then the 10s, and so on. The order of the numbers doesn't change. This ability is what makes the radix sort work. Okay, so it's a sorting algorithm that is you can do it in parallel because you're looking at each digit position separately, so you can do it quickly. Do you guys know about radix sorts? 16 by 16 is also the macro block size for MP4 and H.264. Seems to be a sort of magic number for image compression or representation. Interesting. Yeah, I think it just comes down to 32 is too big and 8 is too small. Sorting problem to smaller, more manageable steps. GPUs can then use their spatial processing power to handle these steps super quickly. Okay, so basically just some fast sort on the GPU. There's no additional per pixel or ordering of points, and blending is performed based on this initial sorting. Or alpha blending can be approximate in some configurations. However, these approximations become negligible as splats approach the size of individual pixels. Interesting. So these splats are tiny. It's like multiple times through this paper. Like in my mind, I always feel like these Gaussians are big, but it's like multiple times they've kind of made references to the fact that these little Gaussians are actually very, very small. We found that this choice greatly enhances training. We produce a list for each tile by identifying the first and last depth-sorted entry that splats to a given tile. We launch one thread block for each tile. Each block first collaboratively loads packets of Gaussians onto shared memory, and then for a given pixel accumulates colors and alpha values. Interesting. So then, once you have this order of here are all the Gaussians in this tile, sorted from the first Gaussian to the last Gaussian, first Gaussian to the last Gaussian, then we're going to actually do it, we're going to do the alpha blending, but accumulating it from both sides. So I'm almost like a kind of like a start from the end, start from the beginning, and then just meet at the middle. Maximizing the gain in parallelism for both data loading and sharing. When we reach a target saturation, the corresponding thread stops. Okay, so basically keep adding these Gaussians until eventually you get to a amount of opacity or saturation that is high enough that it's not worth looking at the Gaussians behind it because you wouldn't be able to see them anyways. So actually very similar to kind of what's happening here with the nerf, where once you get to a certain level of opacity, you don't actually give a shit about what's behind. You don't need to sample the points after that because you're not going to be able to see them. So like here, this ray 2 that's going through here, once you get to this point here, you can actually stop and you don't need to sample any more points along that. So similar thing that they're doing here, that once you get to a certain amount of alpha, to a certain saturation, then you can basically stop. But that also means that because you're also doing it from the back, you're potentially wasting a bunch of compute. Right, because instead of doing it from the front and the back and then stopping once you get to an alpha, couldn't you just do 2 of them at the same time? Threads in the tile are queried, and the process of the entire tile terminates when all pixels have saturated. Appendix C. Sorting. Our design is based on the assumption of a high load of small splats. We optimize this by sorting splats once for each frame using radix sort. We split the screen into 16 by 16 pixel tiles and create a list of splats per tile. This results in a moderate increase in Gaussians. However, it's amortized by the high parallelism of an optimized GPU radix sort. And this is the original badass dudes that implemented a super fast radix sort on the GPU. We assign a key for each splat with up to 64 bits, where the lowest 32 bits encode its projected depth and the higher bits encode the index of the overlap tile. So you're going to have a bunch of these splats. Each splat is going to have a key, which means you're going to have some lookup table of all the dictionary, of all the Gaussians, right? All the Gaussians are going to have the actual properties of that Gaussian, and then a key that tells you, or that allows you to very quickly get that property if you know what the key is, right? That's what a hash map is all about. And that key the first 32 bits of the total 64 bits that you're wasting on that key, maybe not wasting, but that you're using on that key, are the depth, and then the other 32 bits are the index in the sort. The exact size of the index depends on how many tiles fit in the current resolution. Each depth ordering is thus directly resolved for all splats in parallel with a single radix sort. We can efficiently produce per tile lists of Gaussians to process by identifying the start and end of ranges in the sorted array with a same tile ID. This is done in parallel, launching one thread per 64-bit array to compare its higher. Yeah, so this is actually probably why they don't move the Gaussians, right? So at the very beginning of this paper, I asked myself, I was like, why are they creating and deleting Gaussians rather than just moving around a fixed set of Gaussians? And I think the reason they're doing that is because they don't want to move Gaussians from one tile to another, right? If you move a Gaussian that's in one tile and now it's in a different tile because it's kind of drifted away from that, that's going to be really annoying because you're going to have to redo this sort, because this sort is kind of indexing them based on specific tiles. So this is probably why they are doing the thing where if it moves too much, then actually just clone it and make a new Gaussian. Does completely eliminate sequential primitive processing and produces more compact per tile lists to traverse. Yeah, and then you can basically render each tile individually, which is the whole point. Here's how you software rasterization of 3D Gaussians. And here's how you can do it in parallel, right? You have this loop here, this for loop here. For all tiles T in I, do this. For all pixels I in T, do that. So you can parallelize this tile step here. And this blending is also much faster, right? So in a nerf, for example, in a nerf you'd have this for loop because you have to do it for all pixels, but in a nerf, for every single pixel, not only do you have to sample, you have to basically perform inference on a multi-layer perceptron, and that's going to be super slow. But here you don't need to do that because these are just Gaussians. Okay. Coming into the end here. Details of sorting. During rasterization, the saturation of alpha is the only stopping criterion. In contrast to previous work, we do not limit the number of blended primitives and receive gradient updates. We enforce this property to allow our approach to handle scenes with arbitrary varying depth complexity and accurately learn them without having to resort to scene-specific hyperparameter tuning. Maybe, I mean, the set of hyperparameters that they defined up here, like, these are scene specific in a way, right? Because they're specific to the data set that they've tested this on. I'm sure you could find a data set and scenes that are weird enough and different enough that these thresholds, these position thresholds, these alpha thresholds are no longer applicable. So I don't know if they actually did get something that is entirely not scene specific hyperparameters. I think they're still specific just to the data set that they've evaluated it on. We must therefore recover the full sequence of blended points per pixel in the forward pass. One solution would be to store an arbitrary long list of blended points per pixel in global memory. To avoid the implied dynamic memory management overhead, we instead choose to traverse the per tile list again. We can reuse the sorted arrays of Gaussians and tile ranges from the forward pass. Okay, so when you're doing this backward pass, you need the full sequence of points in the forward pass, and either you could store that in global memory, and what they mean here by global memory is the memory on your motherboard, the computer RAM as it's normally called, as opposed to the GPU memory, which is the VRAM. It's also that the GPU memory is sometimes called a VRAM. So rather than having to store these values in the RAM, load them back into the VRAM, you can do this fancy thing here so that you don't have to we now traverse them back to front. So you do front to back and then back to front. So little speed up tricks like this, that's where the money's at. Traversal starts from the last point that affected any pixel. The loading of points into shared memory again happens collaboratively. Each pixel will only start, overlap, testing, and processing of points if their depth is lower than or equal to the depth of the last point that contributed to its color during the forward pass. Computation of gradients described in Section 4 requires the accumulated opacity values during the original blending process. Rather than traversing an explicit list of progressively shrinking opacities in the backwards pass, we can recover these intermediate opacities by storing only the total accumulated opacity at the end of the forward pass. So, I mean, this is kind of hard to understand, but it's basically there's just a bunch of little tricks here that they're doing in the kind of order of operations here for the forward pass and the backward pass so that they don't have to kind of store things in global memory, go back and recompute things that they've already computed, and so on. Each point stores the final accumulated opacity in the forward process. We divide this by each point's alpha in our back to front traversal to obtain the required coefficients for gradient computation. Right, so the opacity alpha is basically roughly telling you how much that particular 3D Gaussian or point is contributing to the final color of the 2D image that you're using for your reconstruction loss. So if your reconstruction loss is saying this pixel right here, it should have been green and instead it's light green, well, that gradient signal needs to get propagated into the right Gaussians, right? So there's probably going to be one Gaussian that has a high alpha that is mostly responsible for that final color of the pixel in that reconstruction loss. So the alpha is basically telling you how much gradient different Gaussians are going to get. We next discuss some details of implementation, present results, and the evaluation of our algorithm compared to previous work in ablation studies. Actually, now that I'm thinking about this, this is probably, there's a lot of like weird dynamics that you could have here, right? Because you can envision kind of like these mode collapse kind of situations where like there's one Gaussian that has a very high opacity and the neural network just keeps trying to change the color of that one Gaussian to match the color of the image rather than trying to create that color from multiple different Gaussians that are more transparent, right? So there's like there's a lot of like trickiness here, a lot of kind of like pitfalls in this optimization process that I feel like they just kind of like magically works, but I don't know. I guess these regularizations that they do here with the like splitting the Gaussians and pruning the Gaussians and getting rid of the ones that are too transparent, I guess those somehow prevent these types of errors, but it's kind of crazy that it still manages to find sets of Gaussians that collectively create the final image rather than just ending up trying to over optimize a single Gaussian that makes one pixel look as good as possible. Okay. Implementation. So that's the technique, and now we're going to basically compare. So this next section here, they're just going to talk about how it compares to other approaches. So let's see. Comparisons of ours to previous methods and corresponding ground truth images from held out test views. So held out test views just basically means that these are not part of the training set. These are separate scenes that have never been seen before. From the top down, bicycle garden stump counter room from the MIP Nerve 360. So this is the data set. Playroom, blah, blah, blah. So we have the ground truth, instant NGP, ours. It's kind of hard to tell here, but I mean, they kind of like mostly look good. You can see here how here they're pointing out the fact that this wheel has a bunch of spokes, and then here the MIP nerve kind of loses track of those spokes. Right here, you also lose track of the spokes. Those are the fine features that they talk about. Here they're showing you how the window in the background, instant NGP, kind of becomes this fuzz of Nerf fuzz, smear, whatever you want to call it. Here it's much more accurate. But like even this, like how the fuck are they doing that, right? Like every single one of these bricks is a Gaussian. Like how do you, the Gaussians only have a single color. So like how are you getting a kind of a tile look where you have a red, white, red, white, red, white, red, white? How are you getting that? It's like we're talking, like, I think it's just because they're using millions of Gaussians. That's the reality. Same kind of thing, fine structure, fine structure. You get that kind of like patented, or like that same kind of Gaussian, or not Gaussian, but that same kind of like weird blurring, misty kind of effect that you get in Nerfs. Here you don't get it. Gaussians are all you need. Yeah, that's why I think this paper is pretty awesome. It's just the Gaussians are just such a good, aesthetically pleasing prior to use. See, 7K iterations, so 7,000 iterations of their optimization process. How many Gaussians are there? That's kind of more what I'm interested in. Like, how many total Gaussians are there? Quantitative evaluation compared to previous work. Okay, so you have R's 30K, R's 7K. Total training time 41 minutes versus a Nerf is 48 hours versus instant NGP is about 7 minutes, so a lot faster. It's also a lot smaller. Yeah, so that's another thing to think about here is that this technique is, or this Gaussian technique is storing a huge amount of Gaussians, more Gaussians than there are pixels probably. So every single one of those, right? Think about an image like a 256 by 256 image has 256 by 256 pixels, which means that there's 65,000 total pixels. Each of those pixels is 3 RGB, and then if you're encoding that with a uint 8, there's the megabytes, right? But let's say you have 1 million Gaussians. For each Gaussian, you're storing a 3 by 3 covariance. You're also storing a, let's make this bigger. You're storing a 3 by 3 covariance. You're storing a mean, which is 3 numbers. You're storing an opacity, which is 1 number, and you're also storing the spherical harmonic coefficients for the color, which I think is probably something like 3 numbers. You know, you can get a huge amount of, and let's say you're storing each of those numbers as uint 8s, which is probably even, they're probably using a higher data type. But yeah, your memory usage is going to be really high. Compare that to something like a Nerf, right, which is basically all you're storing in the Nerf is a tiny little multi-layer perceptron. So that little multi-layer perceptron, there's not a lot of weights in that, so it's obviously a lot smaller. So that is one negative, I guess, is that they never talked about the total size of the actual final scene representation. It does seem that because you have to store all these Gaussians, you might end up having a much larger size than the Nerf. Right, look at these Nerfs, 8 megabytes versus basically 100 times that. Interestingly, planoxels, which is also kind of this point-based approach, also huge memory cost. So basically, all these point-based approaches have a huge memory, like the final scene representation has a ton of parameters, or they're not really parameters because they're kind of points or Gaussians, whatever you want, but you have to store all of those. So it's like it's a more explicit scene representation, so it takes more memory passing that around. If you had to store that, like, you know, that could be a negative. Maybe you do want a tiny ass little Nerf, right? 13 megabytes, 8 megabytes. So it's interesting how, like, yeah, you're getting better, higher quality than the nerfs, but the nerfs are tiny. So the level quality of billions and billions of Gaussians finally use that compute. Yeah. You could, so I mean, like, think about it this way though. Like, what if I took the nerf approach and I took the little multi-layer perceptron in this nerf, and rather than being like 3 layers of 256 parameters each, or 256 neurons, what if I used this giant, like 10 billion parameter transformer instead of this little multi-layer perceptron? You know, like, then have a much higher memory, but I bet you the quality of that would be absolutely insane. You know? So there is kind of a fundamental kind of, the more explicit your scene representation is, maybe the more quality the reconstructed views are, but you're spending a lot more memory to store that more explicit representation. Okay, and then here you have peak signal to noise for synthetic nerf datasets. I'm not even going to look at this. This is basically garbage. Like, synthetic dataset, and it's a PSNR, which is kind of a garbage metric. So we implemented our method using PyTorch framework. So PyTorch, obviously very popular nowadays. I think it's pretty much the go-to. If you're still using TensorFlow, you should complain to your boss that you guys should be using PyTorch, or at least JAX, if you're somehow dead set on Google products. Use the NVIDIA Cub sorting routines for the fast radix sort. Also built an interactive viewer used for interactive viewing. I haven't even looked at this GitHub repo yet. Maybe, honestly, I'm a little bit intrigued, so maybe we do go ahead and look at this and we'll see what the quality does. Source code available there. We use the warm-up, the computation in lower resolution. We start the optimization using 4 times smaller image resolution. We upsample twice. Okay, so it's a little bit more complicated than we even thought. They're running this optimization process using a smaller image and then upsampling it. That's annoying. You don't want to have these type of like extra little tricky details like that. Spherical harmonic coefficient is sensitive to the lack of angular information. For example, nerf-like captures where a central object is observed, taking the entire hemisphere. The optimization works well. However, the capture has angular regions missing. Completely incorrect values of the SH can be produced. To overcome this problem, we start optimizing only after the zero order component and then introduce 1 band of the spherical harmonics after every 1,000 iterations. Okay, so they're also kind of slowly rolling out this SH too. So it's like 2 little one weird tricks here of that you have to use in order to optimize and get to a good place, which is not good. Tested our algorithm on 13 real scenes. The synthetic blender dataset, the tanks and temples dataset. All results are reported on an A6000 GPU. What is an A6000? A6000 GPU. An A6000 GPU is around $6,000. How much memory do we have on this bad boy? 48 gigabytes. So it's a 48 gigabyte GPU. That's not too bad. Show rendered video path. In terms of quality, the current state-of-the-art MIP, we compare against this method to the most recent methods, taking every 8th photo for consistent and meaningful comparisons. We use the standard error metrics used most frequently in the literature. I don't think that's a good excuse. They should have gotten a human study, but I know it's an academic group, so you know, academic groups are generally a little bit more poor, so maybe we shouldn't judge them for not having a human double-blind evaluation for quality. Copy the numbers from the original publication to avoid confusion. Average training time, rendering speed, and memory used to store. Slightly larger networks. Okay, so this is actually, the nerf comes in 2 sizes. So instant NGP, instant neural graphic primitive base, and instant neural graphic primitive big is the same algorithm, just two different sizes of nerf. So a slightly larger multi-layer perceptron and a slightly smaller multi-layer perceptron. And you can see how you get a slightly higher SSIM score here using the bigger MLP. Wow, they're really like crushing it on these metrics here though. Look at this, 0.69 to 0.81, 0.84 to 0.7, like they're crushing it. They beat these other techniques on all of these metrics, and these are standard metrics. Maybe I judged them too harshly. We manually downsampled high-resolution versions of each scene's input images to the established rendering resolution for our experiments. Doing so reduces random artifacts. Oh, so whenever they downscale the images, you get JPEG compression artifacts? Why are they not using PNGs? PNG images are not compressed. JPEGs are compressed. So JPEGs are lossy, but PNGs are not. Same hardware, their average training time was 48 hours compared to our 35 to 45 minutes, and their rendering time is 10 seconds per frame. We achieved comparable quality in 5 to 10 minutes. Show visual results for a left-out test view and previous rendering methods. Even MIP Nerf 360 has remaining artifacts that our method avoids. The blurriness and then the fine details such as the bicycle spokes. 100K, here we go, we're finally getting a number for the number of Gaussians. You have 100K uniformly random Gaussians. That's just so many fucking Gaussians. Holy crap. Our approach quickly and automatically prunes them to about 6 to 10,000 Gaussians. And then the final size is about 30,000, or no, then the final size is 200 to 500,000 Gaussians. Dude, what the fuck? It's creating so many more Gaussians than it prunes, right? So you start from 100,000, you prune them down to 10,000, but then by the end, you have 500,000 Gaussians per scene. Jesus. Using a white background. Compactness. In comparison to previously explicit scene representations, the anisotropic Gaussians used in our optimization are capable of modeling complex shapes with a lower number of parameters. I would say this is a little bit more explicit scene representation than they are making it sound like. You know, 500,000 Gaussians, how is that not explicit? Like, there's a Gaussian for almost every single little micro volume in the entire like scene, so that is an explicit scene representation. Capable of modeling complex shape with a lower number of parameters. We showcase this by evaluating an approach against the highly compact point-based models obtained by this. So yeah, I mean, they're saying that, hey, look at us, we can do this in 734 megabytes as opposed to the Planoxels, which is about 2 gigabytes, but 734 megabytes is still way more than 13 megabytes. So this is definitely more of an explicit scene representation than something like a Nerf, which is definitely much more implicit and much smaller. Obtained by space carving, optimized until we break even. Usually happens within 2 to 4 minutes. Surpass the supported metrics in 1/4 of the point cloud, resulting in an average model size of 3.8 megabytes as opposed to their 9 megabytes. Ablations. Okay, so now this is going to be a more interesting section. Here they're going to talk about which things end up mattering the most. We isolated the different contributions and choices we made and constructed a set of experiments to measure their effect. It's a very nice definition of an ablation study. Blah, blah, blah. Initialization from SFM. So how important is this SFM point cloud initialization? Uniformly sample a cube with equal size 3 times the extent of the input camera's bounding box. Okay, so rather than starting from the points that are coming out of this SFM, let's instead start by just uniformly sampling the 3D space with Gaussians. Okay, so this is uniformly sampling 3D space, and this is starting from the SFM. So I mean, it's actually pretty good. Like, this actually kind of gets most of the parts correct, but you can see how this kind of vine in the background is definitely way cleaner in the SFM points. Okay. Area is not well covered. The random initialization method appears to have more floaters than cannot be removed. Synthetic nerf does not have this behavior. Densification. Okay, so now let's see 2 densification methods, the clone and split. Which one has the best results? So we have no split, no clone, and then clone and split. So the split and the clone is how they're adding and removing the Gaussians. I guess not removing, just adding Gaussians over time. And we know here that they're going up to 500,000 Gaussians per scene from 100,000. So there's a lot of splitting and cloning happening. It's not like this is like a rare occurrence in the optimization process. The splitting and cloning is happening constantly. So if you don't split and you only clone, you get like these weird like mist art, like kind of like the foggy nerf misty effect. If you clone, or if you split but don't clone, then you kind of start losing out on the fine details, like you get here in the spokes, and cloning and splitting gives you the best result. Okay. It's the next thing they compare. So the next thing they look at is unlimited depth complexity of splats with gradients. We evaluate if skipping the gradient computation after the end frontmost points will give a speed without sacrificing quality. So you have these Gaussians and you've ranked them according to which one is closer to the actual view plane. So technically, could you just clip out the last Gaussians in that ranked list, right? They're going to be way in the back. They're probably not going to be very visible. Why don't you just get rid of them, right? Why don't you just only push gradients into the Gaussians that are at the very front of this ranked list, because those are going to be the ones that, even if they have a tiny little alpha, they're still going to be contributing all of that alpha to your final image, versus the Gaussians that are all the way in the back, you're not going to be seeing them. So even if they have a high alpha, you're probably not going to see them. So can we get better speed by just not calculating the gradient for the ones in the back? Led to unstable optimization. If we limit the number of points that receive gradients, the effect on the visual quality is significant. So the left is, they limit it to only the first 10, and then the right is the full method. So it does seem to matter, which is kind of interesting. It means that, what this means to me is that the alpha is probably very small. There's not many Gaussians that have a high alpha. Most of the Gaussians have a medium alpha. It could even be the case that what appear to be hard surfaces are actually multiple Gaussians that are more transparent. I don't know, that's just my guess, but TLDR, it's not better to clip. Anisotropic covariance. An important algorithmic choice is the method of the optimization for the full covariance method for the 3D Gaussians. Seems quite related, Sue Bronsu with a question. But in 3D, there's a new paper, Diffusion with Forward Models. Can you please do that next? I can definitely try, man, but there's a lot of people that want papers. Tomorrow I actually have a completely unrelated thing. It's called MetaGPT, but it's kind of the top GitHub trending repo, so I figured I should do a video on it. Okay, back to this. We perform an ablation. We remove the anisotropy, which is the looks the same from many angles by optimizing a single scalar value that controls the radius of the 3D Gaussian on all three axes. Right. So what if these 3D Gaussians, rather than having three separate covariances, aka the radius of that little ellipsoid, there's three separate axes for that. What if you just had one? Right. So all you could control was just whether it was a big ball or a little ball. The optimization results are presented in Figure 10. We observed that the anisotropy significantly improves the quality of the 3D Gaussian's ability to align with surfaces. Yeah, so obviously it makes sense that you're going to get a much better result if you can have these kind of weird ellipsoids that are kind of shaped and can be very long and thin, or they can be very flat and kind of like this, versus if you just are trying to make this out of Gaussians that are all forced to be little spheres, little balls, it's not going to be as good, right? And then finally, spherical harmonics. Finally, we use the spherical harmonics improves our overall PSNR since they compensate for the view-dependent effects. Where's this one? Table 3. Okay, they don't have a subjective picture for the ablation study on the spherical harmonics. Our method is not without limitations. In regions where the scene is not well observed, we have artifacts. That's going to happen in anything where you're using this SFM as a starting point. Even though the anisotropic Gaussians have many advantages as described above, our method can create elongated artifacts or splotchy Gaussians. I love how they use the word splotchy. We occasionally have popping artifacts when our optimization creates large Gaussians. This tends to happen in regions with view-dependent appearance. So popping is just when you're kind of like you're moving through the camera positions as you're saying, okay, render it from this camera view, render it from this camera view, render it from this camera view, and like you're saying render it from this camera view, render it from this one, and then suddenly poof, this like big Gaussian appears, and then you move it just a little bit and then it disappears. So one of the reasons for these popping artifacts is the trivial rejection of Gaussians via a guard band. Right, so we saw that the rasterizer, when it's choosing which Gaussians to sort for each tile, it actually gets rid of Gaussians that are far away from the tile. Would be to alleviate. Another factor is to simple visibility, which can lead to Gaussians suddenly switching depth and blending order. It's kind of weird. Why would they suddenly switch? Could be addressed by anti-aliasing, which we leave as future work. Currently do not apply any regularization to our optimization. I don't know about that. I think that these are regularizations. The shit that they're doing with the adding Gaussians, removing Gaussians based on these like thresholds, that to me, that's a form of regularization. You know? I think what they're referring to here is that they don't have an extra regularization term on the actual reconstruction loss. The reconstruction loss is just L1 plus the structural similarity. But they could add extra things on that. While we use the same hyperparameters for our full evaluation, early experiments show that reducing the position learning rate can be necessary to converge very large scenes. Yeah, so you probably want to use a different learning rates and gradient clipping for the different parts of these Gaussians, right? I would assume that the color of the Gaussian, like you probably want to take different gradient steps for the alpha than you do for the position, which is kind of what they're talking about here. Or maybe for the position, you want to be able to take big steps, move these Gaussians around a lot more. Even though we are very compact compared to previous point-based approaches, our memory consumption is significantly higher. That's no good. During training of large scenes, peak GPU memory consumption can exceed 20 gigabytes because you have to put all these fucking Gaussians in memory versus the NERF is a lot smaller. However, this figure could be significantly reduced by a careful low-level implementation of the optimization logic. There you go. Here's your next paper. Make a low-level optimized implementation of a 3D Gaussian splatting rendering approach. require significant GPU memory to store the full model and an additional 30 to 500 megabytes for the rasterizer, depending on the scene size and the image resolution. There are many opportunities to further reduce memory consumption of our method. Compression techniques for point clouds is a well-studied field. It would be interesting to see how such approaches could be adapted in our representation. More potential. There's a lot of interesting... The same way that whenever nerfs came out, there was like a huge explosion of possible research directions. I feel like with this, it's the same kind of thing. There's so many different things you could do differently and see if it works better or not. This is called the Dr. Johnson scene down here. I guess, what the fuck is this? Is there like Dr. Johnson scene? Is there like some... Okay. It's probably the house of someone called Dr. Johnson. Alright, finally we made it to the end, guys. Discussion and conclusions. Hype. We have presented the first approach that truly allows real-time, high-quality radiance field rendering. Seems a little bit grandiose. In a wide variety of scenes and capture styles while requiring training times competitive with the fastest previous methods. None of this is explicitly wrong. It's just a little bit... It's worded and phrased in a way that makes it sound better than it is. But pretty much every paper does that, so that's not necessarily unique. Our choice of a 3D Gaussian primitive preserves properties of volumetric rendering for optimization while directly allowing fast, splat-based rasterization. Our work demonstrates that, contrary to widely accepted opinion, a continuous representation is not strictly necessary to allow fast and high-quality radiance field training. So their representation is not continuous because it's a bunch of discrete Gaussians. Majority of our training time is spent in Python code since we built our solution in PyTorch. So it's going to be slow as shit, versus if you wrote this in Rust, be way faster. Only the rasterization is implemented as optimized CUDA kernels. We expect that porting the remaining optimizations entirely into CUDA, as is done in Instant NGP, could enable significantly further speed up for applications. Unfortunately, everyone who knows enough CUDA to write optimized CUDA kernels is getting paid millions of dollars to work on large language models. So there's definitely a drought of people who know enough low-level programming to write this kind of shit. They're probably not going to be spending their time working as postdocs in some French university lab, which is the issue. We also demonstrated the importance of building on real-time rendering principles, exploiting the power of GPU and the speed of software rasterization pipeline architecture. These design choices are key, providing a competitive edge in performance. It would be interesting to see if our Gaussians can be used to perform mesh reconstructions of the captured scenes. Yeah, so, I mean, I would say, why do you care about the mesh? Like, I think meshes are going to eventually go away, but a lot of people use nerfs, and then they use nerfs to create a mesh, and then that mesh is what they use for their actual video game. Like, because most video games, most things like that, you're going to actually need a mesh. So even though people are using nerfs right now, like you can't actually use a nerf in a video game. So you have to turn it into a mesh and then be able to use it in a video game. So that step of going from a nerf to a mesh, even though it seems kind of nonsensical, because it's like, if you have the nerf, just use the nerf. People still want to be able to do that. So you could do something similar here where, hey, we have this representation of our scene as a bunch of Gaussians. Could you turn that into a mesh so that I could bring it into my computer game over here? So that could be another thing that you could be interested in doing. Aside from practical implications given to the widespread use of meshes, this allows us to better understand where our method stands exactly in the continuum between volumetric and surface representations. This is kind of interesting. It's one thing that they could do to answer this question is show us the distribution of these Gaussians. Like, are these Gaussians just all on the surface of the object? Are they like within the entire object? Or, you know what I'm saying? Like, if I had a 3D Gaussian splatting representation of this black bottle, are all of the Gaussians on the surface of the bottle and then the inside is just a bunch of empty space? Or are they kind of like more evenly distributed? right? Like, what do the alpha values look like? Do you have like one Gaussian that has like basically that's like perfectly opaque and then everything behind it is empty? Or do you have like kind of like a layer of Gaussians that have kind of like more see-through, and it's kind of like cumulatively they become the hard surface? So I feel like I would have liked to see like a plot of that, of like, show me where all these Gaussians are. Show me the 3D position of these Gaussians for an object, and then is it empty? Like, what are the alpha values for those, and so on. In conclusion, we have presented the first real-time rendering solution for radiance fields with rendering quality that matches the best expensive previous methods with training times competitive with the fastest existing solutions. Adobe for generous donations. Interesting. So this is like an Adobe-funded lab. Cool. That's it. That's it, guys. Optimization and densification. We're already looking at these per scene error metrics. Okay. Let me take a big sip of this yerba mate, and then let's do a paper summary. If you guys have any questions, now's the time. Where else can we use Gaussians? NLP? I'm trying to think of like what would a Gaussian represent in NLP? I mean, I don't know. I don't know that I can't think of anything off the top of my head, but like a Gaussian is this, right? It's just, where is it? It's just that it's a Gaussian. maybe you could embeddings. Maybe you could do something like the embedding of the word itself. Like whenever you're using a tokenizer, it's like a Gaussian in some multi-dimensional space. Like maybe something like that. I don't know. That'd be really fucking weird. But hey, who knows? Maybe it works. You're using 3D Gaussian here. The whole point of this paper is you're using 3D Gaussians as a prior for 3D objects in 3D space, but you could envision using n-dimensional Gaussians as a prior for n-dimensional embeddings of tokens in an n-dimensional space for natural language. I don't know. It's on you, Christopher. You got to go out and do that. Do it for the internet points. The problem with NLP is that even if you discover an approach that's better, you're never going to actually be able to show that it's better because you're comparing against people who are spending millions of dollars on their methods, right? So it's like, it could be the case that there's all kinds of better ways of implementing a transformer such as RWKV, right? But the problem is that they're never going to have the same training budget, the same data set, and the same amount of engineering effort put into their technique as the current techniques. So it seems like the current techniques are always beating theirs, even though in theory, if we were to use the same data sets, the same amount of training budget, and the same everything, there could be way better algorithms that some other random person invented. It's just we're not using them because we're not using them. Yeah, there's so many things like that. Okay, let's summarize this paper though. So today we read 3D Gaussian Splatting for real-time radiance field rendering. This is a new type of NeRF, basically. So in a NeRF, what you're trying to do is represent a 3D scene. So you have 3D scenes, which are basically, here you have a bicycle in front of this, whatever this is in this path, and you're trying to be able to say, hey, I have a bunch of pictures of this bicycle, and I want to be able to create new pictures of this bicycle, right? So those novel views are basically new 2D images from a 3D scene. So we need to figure out a way to represent this 3D scene, and there's a lot of different ways of doing that. So in a NeRF, you're representing it as a radiance field. You're representing it as this little volume, which is then represented by a neural network that says, okay, give me any point in this volume, and I'll tell you what the color and the density of that point is. And that's what a NeRF is. But NeRFs are very slow, and they're slow because you have to basically, not only do you have to train them for an individual scene, but then for every single point inside a ray of, and then for every single pixel of which there's a ray, you have to perform inference on a little neural net. So potentially thousands, millions of inferences just to get the final 2D view that you're interested in. What this paper does is it goes all the way back to the beginning and it says, okay, let's not assume that we have some continuous radiance field that we can evaluate at every single point. Let's instead say that we have a discrete set of points that are Gaussians, 3D Gaussians. And these points, we're going to basically move them around and slightly make them a little bit wider, a little bit shorter, a little bit more fuzzy, a little bit more see-through, right? And over time, we'll be able to represent this scene as this discrete set of Gaussians. And they, here in the related work, they talk about how this is actually more akin to what are called point-based techniques. So point-based techniques like planoxels are representations of 3D scenes that are kind of more explicit. They're, for example, a mesh is a point-based technique. You're storing all these little points and the connectivity between all these little points. What else? Circles are a point-based technique where you're storing all these little points. And in the case of a circle, it has a specific radius and it also has a normal vector. So it's a 3D representation of a scene that is much more explicit. And these 3D Gaussians are much more similar to that than they are to a NeRF, right? And you can see that because later on they show you, they compare to other things, and you can notice how planoxels, which is a point-based method, you need 2 gigabytes of memory just to store every single one of those little points and every single one of those little surface normals. Same thing here, these Gaussians, they say they have 500,000 Gaussians. You need to store the XYZ position of every single one of those Gaussians, the XYZ covariance of every single one of those Gaussians, the color for every single one of those Gaussians, and the alpha for every single one of those Gaussians. So at the end of the day, it takes you 734 megabytes just to store a single scene. So compare that to a NeRF here. These instant NGP, these NeRFs, they're 13 megabytes. They're tiny, right? They're like 100 times smaller. And the reason that they're smaller is because the only thing they have to store is the weights of this little neural net. And that little neural net implicitly stores the entire scene. So this is kind of a point-based method. They're pretending that it's like the better NeRF, but really there's a whole history and there's a rich history of people who have come up with all kinds of other point-based methods. So it's not as novel and unique as I maybe thought it was at the beginning, but it still is pretty cool and impressive. What else? Optimization, density. So they have this kind of general optimization process where they start from structure from motion points. So these are basically guesses as to where your camera is for every single picture that you start from. So for any of these 3D scenes, you're going to have to start from a set of pictures that each have a corresponding camera position, right? And unfortunately, that process of going from a bunch of pictures with camera positions into these SFM points is noisy and not perfect. So NeRFs also do that. NeRFs also start from this kind of SFM points. So they have that same problem. So one thing that both NeRF and this approach suffer from is the fact that they're sensitive to this SFM initialization. But at least in this paper, what they do is they start from this SFM, they basically put a bunch of little 3D Gaussians at all those points, and then they run this reconstruction loss, where they're basically taking these Gaussians, they're kind of shifting them, moving them, they're cloning them, splitting them. So like occasionally they'll split a Gaussian into 2, or they'll combine 2 into 1, or delete some, and then they keep rendering the image with this differentiable tile rasterizer, and then comparing the image that they render with the ground truth image. And they're saying, okay, these two images are the same. And the way that they're doing that is with an L1 loss and a SSIM loss, structural similarity, which is basically, are these two images the same? And if they aren't the same, why aren't the same? They're not the same because of this particular pixel. Okay, what does that particular pixel correspond to? Oh, it corresponds to this particular Gaussian. Okay, that particular Gaussian, what does it correspond to? Oh, you need to change the color slightly this way. Okay, we're going to change the color slightly that way. And so over time, you keep pushing these gradients, pushing these gradients, pushing these gradients, and eventually these 3D Gaussians kind of start shaping the rough shape and color and appearance of your 3D scene. So that's the optimization process. What else? This optimization process has, unfortunately, a lot of hyperparameters. That's one thing that I didn't like, is that they have like a specific threshold. So every 100 iterations you go through, and if there are any of them that have below this amount of transparency, you delete those. Every X amount of time or X amount of steps, you look at the position between two, and then you do this. So like all these little thresholds and position and little one weird tricks, and there's even more that they don't even include there that they include later here, where they're like, okay, well, first you start with a slightly smaller version of the image, and then you slightly increase the image. So there's a lot of little tricks that they're using in this optimization process, which isn't great. You know, I think it's much better if you have a cleaner, simple optimization process that doesn't have like 10,000 different little threshold tricks and steps. But this is not by far the worst I've seen. This is like pretty standard. What else can I talk about? Yeah, and then I think the other kind of big thing that they do here is this tile rasterizer. So this tile rasterizer, first of all, it's differentiable, which means you can back propagate. You can chain rule backwards, which means you can get the reconstruction loss from the image and then go all the way back to the actual properties of the 3D Gaussian. But the reason this tile rasterizer is great is because it's breaking up the image into these tiles and then using this very fast sorting algorithm that runs quickly on a GPU that allows you to sort these Gaussians from which Gaussian am I going to see first, which am I going to see second, which am I going to see third, which am I going to see fourth, and so on. And this sorting is fast enough that you can basically, this whole process runs quickly. And that's compared to the ray marching, which is a different type of algorithm, rendering algorithm that is used in NeRFs, and the ray marching in NeRFs is slower when you actually try to implement it in the real world compared to this tile rasterization, which is what they do here. So a huge component of why the speed is fast here and why this is much faster and you can get real-time rendering is because the way that this tile rasterizer works out, you can do it very quickly on a GPU. Yeah, and then they compare it to NeRFs and planoxels, which is another kind of point-based technique, and it does seem to work quite well. You know, the results speak for themselves. You get much better reconstruction of fine details here. You get a lot less of this kind of blurring that you usually see on NeRFs, where you get this kind of like fuzzy, misty effect, and it's quite clean. And that's basically it. You know, they do some ablations, and they point out a bunch of future possible research directions, but overall, I thought this was a pretty interesting paper. It was well written, very clean. I think it's a little bit, they try to like lead you in to think that they've done some crazy shit, and then you realize that this is just a point-based method that works because it kind of uses a fast GPU radix sort. But pretty cool stuff. Mojo is probably the destination to help with speedups on this. Yeah, so Mojo is basically Python, but fast Python. I think it's being led by the guy who wrote Swift at Apple. Mojo, Swift, right? Yeah, Swift creator, Mojo. So I don't know. We'll see. Mojo so far is just a bunch of promises and hype. Like, I haven't actually seen them like do anything in practice with it yet, but who knows? This is a good example of something that could use Mojo, right? They say that they implemented everything in Python, so if they could just take that same Python file and use Mojo instead, maybe it does result a lot faster, but I feel like there's probably the better way to do this would just be to implement it directly in CUDA kernels, right? Directly in a more performant language than Python, and it would probably be super fast. But who knows? Maybe this is the 3D scene representation that we'll see in video games. Maybe whenever in 2030, when you're sitting in your VR headset and you're moving around in like a NeRF, or not a NeRF, you're moving around in some 3D world, maybe the underlying representation of that 3D world is not a bunch of textures not a bunch of meshes with textures and lights that are bouncing lights off the object. Maybe the underlying representation will be something like this. Maybe it'll just be this giant set of little Gaussians. You know, and maybe one extra point here before I go away. sorry, I'm like flying through here, is that one thing that NeRFs and these techniques, none of the techniques in this paper address, is that all of these are for static scenes. So dynamic scenes, scenes that have a time component, right? Like you pick up the bike and you do something, right? Like those don't exist yet. So right now we're just saying, okay, well, 3D Gaussians compared to NeRFs, like the quality is higher and it renders a little bit faster. But at some point, we're going to want to have dynamic scenes, like movies, right? Like 3D movies. So is it the case that 3D Gaussians are a better prior once you start putting time in? Or is it the case that a NeRF, which is a little neural net, is a better prior when you start putting time in, right? So once you start actually adding the dimension of time and you want to have a 3D scene over time, it could be the case that 3D Gaussians are a better prior and they make certain things easier, right? And it results that, oh, if you just add an extra time component over here, then you can still use this tile-based rendering and it's actually just as fast, versus if you try to add time to a NeRF, it just blows up and it's terrible. So I don't know, it could be the case that for some other unknown reason that we don't know yet, the 3D Gaussians are way better than the NeRFs, but so far they're just basically a little bit more memory, a little bit faster, and a little bit higher quality. And that's that, guys. I need to go, but I appreciate the time. Thank you, John. Thank you, Christopher. Thank you, Luke. Thank you, Subransu. Thank you, Navjot. Thank you, Scott. Thank you, everybody. Bob Plan. Everybody who came, everybody who commented. Thank you, Ed. Thank you for the questions. Thank you for the comments. Thank you for your interest in science. I don't know, whatever Huberman says, but thanks, guys. You guys have a great Monday, and see you guys later. Peace.